Okay, hello everybody, and welcome to our strong interaction and hadron physics session. Um, I would like to remind everybody to please stay muted unless they are asked to unmute themselves. We would also ask the speakers to please stick to their time slot because we have a very tight schedule. The talks will be 15 minutes, which includes 3 minutes of discussion time. So please leave some time at least for 1 or 2 questions if possible. And if the first speaker can put their slides on, that would be great. That would be Armando Bermudez Martinez. Are you there?
Yes, I'm here. So thanks a lot for the invitation to this event. So yeah, so the talk title is the PB pattern branching method and multi-jet production. So, but before talking about the pattern branching method, I just want to have a few words about transfer momentum dependent pattern distribution, so TMD. So this has been a subject of development and research in recent years. You can check the reference on the up right corner. And why is this? Is because it is important for small transfer momentum phenomena description, but also for small x phenomena. And for example, it's important in different observers like Trajan, low QT, or semi-inclusive DIS. Why is this? So because one have to take into account not only transfer momentum effects from intrinsic KT, but also from the evolution. So they brings me to the pattern branching method, which gives a solution to the evolution equation of transfer momentum dependent pattern distributions, not only also for collinear PDFs. It includes a resummation of so-clue on that, not only a leading log, but also next to leading log. So the solution that it gives is valid at leading order, next to leading order, and next to leading order. And it allows to determine the TMDs from the fully exclusive solution that it gives. And also by its power evolution, one can fully determine TMD, the corresponding TMD shower. You can check the reference on the right. So in this way, one consistently treats the perturbative and non-perturbative transfer momentum effects. So a few more words on this, what is basically happening. So here I show the first solution of the iterative solution to the TMD evolution. And you can follow the color code to see what is happening in the evolution of the initial state. So the branching is given by the splitting function, and also the evolution from a scale to the other scale is driven by the corresponding Surakov factor. So from this, we have, by using this method, that the kinematics of the splitting is fully known. This makes it fully exclusive. So the physics is encoding the mapping of the evolution variables to the splitting kinematics. The TMD is obtained from the cumulative KT of the branching in the forward evolution of this equation. And the initial state shower is fully determined by the TMD and its powered PV evolution. So achievements of this method, so you can see, so you will have more details on this by Schwinn and Jindrich in the following days. And but I will just comment some of them. So so we have determination of transfer momentum dependent pattern distributions and its evolution. Is valid not only for on-shell, but also for off-shell matrix element calculations. So this is crucial for those. It has been successfully combined with MCR. You can check the reference on the right. And it gives an excellent description of low PT hydrogen spectrum. This you can see in the plot on the left corner. And but not only that, so it also gave the first simultaneous description of both low and high mass spectrum, as you can see also on the right hand plot, in which the Phoenix experiment result is shown compared to the PV prediction. So, however, we would also want these calculations to be able to describe high PT phenomena. and multi-jet phenomena. And if we see in the, for example, in the CMS publication in which the PV prediction is shown compared to the data, this is a red curve on the left hand plot. And we see that it doesn't agree at large PD of the set, so the recoil is not described. But not only that, so what about, so we have the recoil is not described, but what about the jets that are up to that recoil? So this we see on the right hand side, in which we have the jet multiplicity in set production. And so we see with, apart from the one jet in this case, so the jet multiplicity is not described. So this brings me to what we want. So what we want is to treat perturbative and non-perturbative DND effects by using the PV method in the calculations. Include soft gluon resummation also by the PV method, but also include correction from higher order fixed order calculations. And this is what we lack. And then this is why we have developed a method to combine PV TMDs with multi-jet calculations. Before going to some details of the method, I would just remind what a multi-jet merging algorithm does. So it ideally makes high order matrix elements exclusive by Surakov suppression. By this, you avoid double counting between pattern shower matrix elements. And then this ideally will improve your hard wide angle emissions, and also consequently will describe high PT phenomena ideally. So what I have said is sketched here in this picture. So you have, let's say, the PD of the set, and then you have a resun prediction depicted by the blue curve, and the matrix element, higher order matrix element prediction calculation given by the red curve. You would like, or you would rely more on the blue at a low PT, and you would rely more on the red at high PT, but just a cut would not help you because the matrix element calculation is inclusive, so you have to make it inclusive. One way of doing this is to include a Surakov suppression from the same shower, and by this, then you can have a smooth transition between low PT phase-space regions and high PT phase-space regions. So this gave me to the method. So it's the paper about this method is in preparation. So essentially, so there are a few steps. So first you evaluate the matrix element from the jet cross sections. Then you reweigh the strong coupling according to the shower history. You want to make the because you want to make the transition as smooth as possible. And then after that, then you evolve the matrix element using the TMD PV evolution. Then you shower the events using the backward PV evolution for initial stabilization. Then you apply the MLM prescription in this case between the PV evolved matrix elements and the shower events. So this gives a new merging procedure, which is now applicable to TMDs. So in order to check that everything is going okay, so one could look at the differential jet rate plots, which essentially give you the scale at which N1 jet configuration becomes N jet. So now, a good thing about this observer is that it mimics the merging scale phase space. This means that if you have smoothness in the curve, then this points to the that the merging follows the shower Surakov suppression. And as you can see in the plot, the different multiplicities are separated, or the merging scale divides the phase space for the different jet multiplicities. And by this, then you avoid the double counting. You can look, for example, on the left-hand plot in which zero jet becomes one jet, or the scale at which a zero jet configuration becomes one jet configuration, and at the value of the merging scale, or the logarithm of it, which is 1.3 around. So you see that zero jet multiplicity is on the left, whereas all the others are on the right. So similarly to the transition from one jet to two jet multiplicity on the right-hand plot. So this brings me to some results. So one can check. So if you recall the plot that I showed previously, in which we were not able to describe the high PD scenario for the set PD on the right-hand plot is that result already shown. Now on the left-hand plot, then the new PBMLM prediction in blue is shown, and then you can see now that this region is very well described. And not only that, it is consistent with the low PB prediction at low PT. So we not only cover now a high PT scenario, but also we didn't spoil the nice description of low PT phenomena. So now the overall recoil is described, but what about the number of jets that add up to that recoil? So if you remember, this was not described. This is shown on the plot on the right. Now on the plot on the left, then you have that new PB method, PBMLM method gives a very nice, very good description of the data. You can see the contribution of different samples. So this means that not only the overall recoil, but also the number of jets are described. There's different subsamples that they contribute, as one would expect, more to the corresponding jet multiplicity. So now we have not only the overall recoil, but also the number of jets. But what about the PT of those jets? So let's get more exclusive, or as long as we can. And for that, we show here the PT of the leading jet in set production. When one jet is required, so for at least one jet, this is the plot on the left, and for at least two jets, the plot on the right. And you can see that is that the fine combination of the jet sample gives a very good description of the jet PT. So you can see, for example, on the left-hand side, that one jet sample is the main contribution of low PT, whereas the 2 and 3 jet samples, they take over a large PT. So it's only the fine combination of those what gives the nice description. Similarly to the plot on the right with the 2 jet scenario. So we have a method that that gives a good description of the data for many, not only inclusive but exclusive observables. But what about the systematic? So what are the underlying errors that we or underlying restrictions that we have? So for that, we can vary the emerging scale and look at the different jet multiplicities, or how the different jet multiplicities change. And by doing this, we got that the 10% 10 GeV variation of the emerging scale gives less than 2% change in the jet cross sections. And one have to remember that the standard merging algorithm can give over 10% change for the same variation of the merging scale. So this result is very important, and it tells that the dependence on the merging scale is reduced by treating the transfer momentum in the initial state. So this brings me to my conclusions. So the multiple jet multiplicities evolved with the TMD-PB method have been successfully merged with the new PBMLM method. The differential jet rates are smooth, which implies emerging Surakov suppression that follows the shower. The PBMLM method prediction for the ZPT spectrum reproduces the data in the whole range, and it is consistent with PBMCRN at low PT. The merged predictions for jet multiplicity and also jet PT agree very well with the data. And also this new method gives a lower variation of individual jet cross-section with the merging scale. Lower than the standard algorithms. So as a step forward, so we are looking forward to extending this new method to handle next tolerating order multi-jet samples. Before finishing, I want to maybe you feel welcome to connect to the following link, which is given in the slide for more discussion on these topics. So this will happen after today's sessions, I think around 9 p.m. Yeah, feel free to connect. So thank you very much. It was a pleasure. If you have any questions, remarks, suggestions, ideas, they are very welcome. Thanks a lot.
Thank you very much, Amanda, for this nice talk, and also for being on time. Are there any questions to the speaker? If so, please raise your hand. Okay, if there are no questions from the audience or from the chat.
Sorry, I've just tried to raise the hand. I'm not sure whether this is visible.
No, it's not actually visible. I don't see it. Please just say your name and then ask your question. Sorry. I see it now. Frank Ziegert. Okay.
Yes, my name is Frank. Thanks for this nice presentation, Armando. I have one question on your slide 8. If you could go back to that. So this is a very nice plot to see how well the two sides of the merging match up to each other. And I was just wondering about this, the feature around the merging cut. So I suppose this was with the 23 GB merging cut. So this dip that we see right in the middle of the plot is exactly the merging cut. So if you would now vary the merging cut and look at this distribution, it seems like you would get a rather large variation differentially, right?
Yes, can you hear me?
Yes.
Oh, yeah. Okay. Thank you for the question. And yeah, I mean, if you vary the merging scale here, you will enter in maybe a non-physical exclusive outcome, right? So you will have a non-physical step. So this is why you can use this observable to kind of have a feeling of what is the region in which you are not too so in which you are in the overlapping region between the pattern shower and the matrix element, so you cannot go too away from that. But that's true. I mean, if you vary it here, then you will essentially see a step popping up.
Okay, thanks. So you would say, for example, for a set PT, which this translates into basically almost directly, you would not have a reliable prediction around the 20 GV region or something like this. So you would not trust it too much around this region then.
Yes, I mean the set PT is a bit inclusive compared to the differential jet, right? So if you varied, for example, 10 GV, 20 GV, so you would probably see a step in the differential jet rate, but you will not see it in the set PT because the set PT is too inclusive, I think.
Okay, that would be good to test and see as well. Thanks.
Yes. Okay.
Okay, any more questions? I do have one question, if there is none from the audience. So I believe there has been attempts previously to fit the low PT and high PT spectrum for Dredian in the TMD formalism, and even include higher order corrections, I think by Schimami and collaborators. So are the non-perturbative parameters that you find, can you comment how do they compare to what they find?
Okay. So I'm not very aware of their work. I mean, I've at some point I looked some of it, but what I remember. So for example, here the non-perturbative part of the TMD. This you will see more details in future talks by our colleagues. Is encoded in the intrinsic KT distribution. So you have an initial non-perturbative TMD that then you evolve, and then this is what you feed to the data, right? So now the non-perturbative parameter there. So we have up to now we have a Gaussian distribution for it. This can be, of course, improved. But so the important point is that the non-perturbative width of this initial distribution is of the order of 500 MeV, right? So if you compare that, okay, I will talk about what I have in the top of my mind rather than, excuse me for that, than what you asked. So if you look, for example, at Pythia, so they have also a treatment of non-perturbative intrinsic KT, but the value there is of around 2 GB. And if you move it to another value, then you don't describe anymore, for example, the ZPT spectrum. And also you have to choose different values if you want to describe, for example, the low mass region spectrum. So in our case, this non-perturbative parameter is really in the non-perturbative region. So we have a GeV, so 500 MeV, 300 MeV or so. as the non-perturbative input. Again, this can be further improved and yeah, and
Okay.
we have to look at data as well. And but okay, it's non-perturbative, so it's a non-perturbative region, and it doesn't change with respect to this. Is not tuned, so this is the same value for other predictions that you have seen. And normally this is not the case for other approaches. They have to tune this non-perturbative input. For us, it's not possible, and also the TMD shower depends on it because it follows exactly the TMD evolution, and so it's a bit restricted. So you cannot change much you cannot change at all the predictions that we have. There's no tuning room.
Thank you, Amando. Thank you very much.
You're welcome.
Okay, I think we have to move now to the next talk by Peter. So if you can please take your slides away and then he can put his.
Okay, thanks a lot.
Thank you. Thanks. So the next talk is going to be by Peter Loch on precision measurements of jet production at the ATLAS experiment. Please go ahead.
Yeah. Hi, yeah, thank you for having me. I'm going to give a brief report on the some recent results from inclusive jet measurements with the ATLAS experiment. So jets in ATLAS are, of course, a very nice tool to understand the strong interaction in a wide dynamic range. We do a very inclusive jet cross-section measurement. For that, we can actually use this measurement also to understand the structure of the proton at very high momentum transfers and a few other features of the strong force. And the structure of the proton. We also use jets to test the emission modeling, meaning we're looking at event shapes and see how well they are represented in various generators and compare them to the data we measure. This talk here, we will talk about hard emissions. There's actually another talk by Jennifer Roloff coming up in the same track, looking at a wider spectrum of these things using different tools. We also have measured the running of the strong coupling constant in very high at very high momentum transfer scale. So I want to briefly reflect on that as well. So the jet measurement in ATLAS for run 2 is actually we're still using our good old anti-KT jets with the radius parameter of 0.4. We're using two variations of these jets. One is using the calorimeter signals like in run 1, and then we have the particle flow objects now, which combine the calorimeter and the tracks. For run 2, the reconstruction is very precise. We have order 1% total jet energy scale uncertainties above something like 80 GeV or so in PT. There will be a talk by Eva Hansen in this conference about more details about this, how this is achieved. We prefer particle flow jets. This is shown in the plot on the right bottom because of the better resolution at low PT. The precision measurements we have published is a first measurement of the inclusive jet and dijet cross-section measurement based on the initial data, basically the first year of run 2. And then the hadronic event shape and strong coupling constant measurements with using the full run 2 data set. So as for the inclusive jet and dijet cross-section, the data is collected from the proton collisions at square root of S of 13 TeV in 2015 only. We have a slightly limited dynamic range, 100 GeV up to 3.5 TeV, and we're basically looking only at jets that are within rapidity of 3. There are some selections also for the inclusive dijet production cross-section you can read off the slides. We compare to QCD predictions next to leading order, next to leading order, calculations with non-perturbative QCD and electroweak corrections applied, and we test various PDFs. As you can see from the plot on the bottom right side, even within the limited statistics of this first year data, there seems to be a slight favor for next to leading order calculations arising from the data. So we will follow up on that with the analysis of the full data set. Now, if you look at the event shapes and we measure those now with jets, we basically use those jets as a proxy for the energy flow in the collision. With this measurement, we can test the prediction power of fixed order calculations, pattern shower modeling, and so forth. The shapes we use have clear expectations. For given topologies, all shapes vanish in the in 2-to-2 processes with perfect forward-backward symmetry. The shapes are typically at maximum for uniform energy or transverse momentum distribution, isotropic events, if you want. We can probe these multi-jet energy flows now at very high scales, and we use a measure for the hardness of the interaction, which is basically the scalar sum of the two leading jets. We use multi-jet final states. The selection of these jets, we use only jets above 100 GeV and only in the central region of the detector. We require at least 2 jets in the event, and we require at least a scalar sum of PT of 1 TeV. We present the results as differential cross-sections as function normalized to a fiducial cross-section in the number of jets. The jet shapes, the event shapes we're looking at are a transverse thrust, the minor component of the transverse thrust, transverse sphericity, planarity, and C and D observables that are extracted from the sphericity matrix, sphericity tensor, I should say, for 3 and 4 jet events. All this is studied in HT2 and a number of jet bins. The unfolded data is then compared to various Monte Carlo generators. So if you just want to get a picture, if you have a 3-jet event with a high value of tau, which is 1 minus the transverse thrust, and transverse sphericity, you get a rather isotropic shape, while you in the 5-jet event on the right, you have low values of the transverse tau and the transverse sphericity. So if you look at the fiducial cross-section in terms of number of jets, you see that the modeling of these cross-sections, that actually Pythia performs quite well, basically in the whole dynamic range. You see here the cross-sections in various bins of HT2 and tested with various models. And you can read off the findings yourself on the right-hand side. In general, as for the normalization, it's well predicted at lower jet multiplicity, but there's a large spread in the normalization at higher jet multiplicities. For example, Shirkbot predicts 30% more than data, and Herwig and Metcalfe predict 30% less than data. If you look now at one of these event shapes, this is just an example. In the backup of these slides, you find a few more. This is in the highest, those are the hardest events or highest HT2 bin. And you're looking at the tau perpendicular for various jet multiplicities. And on the left and on the right, there's a comparison to the various models that we consider. Now, we can observe that the evolution with the increasing hardness of the interactions, we have more events with more isotropic flow at softer interactions, and increasing the HT2 yields increased contributions from events with close to back-to-back flow patterns. In the comparison to models, generally the models have fewer isotropic events at lower jet multiplicities. There's slightly better agreement at higher jet multiplicities, but the shapes are really not represented all that well in the full phase space by any of the models. And as a final point for today, I want to reflect on the measurement of the running of the strong coupling constant that we do using transverse energy correlations. So here you can see the correlation function that is actually measured. On the right, you see the results. The result for the inclusive measurement. Again, we use the HT2 variable as a proxy for the hard action scale for the momentum transfer, if you want. The selections of the jets are given below. So we're using, again, our 0.4 jets from particle flow. We require a jet to have at least 60 GeV. We're looking only in the central region of the detector. And we are only considering events that have an HT2 of more than 1 TeV. So together with the transverse energy correlation, we have the associated azimuthal asymmetries, which are shown in the bottom right part, and have also information on alpha S in them. again, we do unfolded data compared to particle level Monte Carlos. So on slide 10, you finally see the results. The boxes indicate the new data points added by this measurement. So we're now definitively reaching into very high TEF scale Q momentum transfers. The determination is done by fitting theoretical predictions to the energy-energy correlation and the asymmetry. We can extract the global alpha S from that at the Z pole. We can fit local alpha S in bins of HD2 and evolve those using the NLO solutions to the renormalization group equations. So with this, now we can test the running. We can compare the running to the predictions. And it's as you can see, this agrees quite well with the predictions, and also the inclusive measurement compares very well with the world average that is derived from the other measurements. So summarizing this very, very brief report. So we have an early cross-section measurement, which has the first test of QCD calculations at next to leading order. We will use the increased precision in the jet reconstruction in LHC run 2 and Atlas to do a full run 2 analysis with the full statistics. And we hope that we can actually particularly push the lower limit in transverse momentum down from the present 100 GeV. For the hadronic event shapes, clearly the observables indicate some deficiencies in modeling of these hard emissions, and probably can provide some guidance on future developments on that front. The measurement of the running alpha S gives a very good agreement with the next to leading order alpha S predictions, with the next to leading order predictions for the running, and it's now fully extended to TEF scales. We have a few more contributions from Atlas at this conference. There will be a larger overview talk by Bogdan Malescu, and Helena Santos will report on the heavy ion jets in Atlas, and Mark Sutton will report on the determination of PDFs in Atlas. Thank you.
Thank you very much for this nice talk as well. And I believe there is a hand raised already by Marek Karlinar.
Yes, the question is about your transparency number 10. Peter, in the caption, it says that you have measured running of alpha S for Q larger than 1 TeV, but if I'm not mistaken, the plots end below 1 TeV value of Q. So do you have something that you can show?
Yes, but the 10 to the 3 here is the value of 1 TeV.
Oh, sorry, I misread the label.
The blue box is basically outside of 1 TeV. So
I misread the caption. Thank you very much. Excellent. Thank you.
Okay, no problem.
Thank you. Any more questions? Okay, I don't see another hand. I just have a very quick question. So I believe for the TEEC, there are some resummation calculations that have been performed by theorists. So I was curious, did you compare to that theory or just to Monte Carlo? I think there is work by Haitao Lee and collaborators on this.
So I think I have to remember now the paper. I was not involved in this analysis, but I think it's a calculation.
Okay.
Yeah, I think it's compared to that calculation. But I will have to confirm. I can only remember it only very weakly. It's actually just out, the paper, so it's a conf note.
Thank you. Any more questions? I think someone else, Matt Leblanc.
Hi. No, I just wanted to chime in on the last question. So they compare to the NLO calculation, okay. And we hope to be able to compare to an NNLO when it is available, but of course we don't have it yet.
Thank you very much, Matt. Okay, so I think we should move ahead to the next talk. So thank you, Peter. And if you can take your slides away, thanks. And I think the next talk will be from CMS, jet measurements at CMS by Christian Baldenegro Barrera.
Cool. Thank you very much for the introduction. So indeed, I'll be presenting recent results like the CMS collaboration on jet-related measurements. So just as a brief motivation, we're in general interested in understanding various aspects of short and long distance behavior of strong interactions at the LHC. So in particular, we can think of tests of perturbative QCD, or also improving our modeling of soft physics phenomena embedded in Monte Carlo generators, or general improvements of the PDFs of the proton, tests of resumation schemes to all orders in alpha S. So all of this is very interesting on its own right. But also as a side effect, it also helps us understand better our backgrounds in searches for new physics with related to strong interactions. So the benchmark process to understand all of these QCD interactions is in jet production, so collimated spray of particles. So today I will be talking more specifically about these three measurements. So the first one is related to the inclusive jet cross-section as a function of the anti-KT distance parameter at 13 TeV. The second one is related to angular and momentum distributions in multi-jet production at 8 TeV and at 13 TeV. And the third one will be on jets separated by a pseudo-rapidity gap at 13 TeV. And again, just to briefly advertise that there are many other studies that are also related to jet production by CMS. And I put here a list in case people are interested in checking it, tuning in with the speakers online or offline. Okay, so I'll jump now to the first topic, which is on the inclusive jet cross-section as a function of R. So the main interest of this is that by scanning different distance parameters, you're sensitive to different components of the jet formation process in QCD. So here, this delta P represents the lost transverse momentum outside of the jet cone in the small radius approximation. And here what you see is that when you go to very small values of R sensitive to your Parton shower evolution effects at small r, then also at small r, you're sensitive to the hadronization effects. And when you go to larger values of R, you are more sensitive to underlying event activity. So if you do a scan like this, you will in principle see a transition between all of these different components of the jet formation process. So these are some technical details about the study at 13 TeV. This is using 2016 data from CMS. The jets, they have rapidities within 2.5 units. So these are central jets. And the transverse momentum starts at about 84 GeV for the jets chosen here. And the main observable is the double differential inclusive jet cross-section ratio in transverse momentum and in rapidity, where we take the ratio in the numerator as while varying the distance parameter R from 0.1 and up to 1.2 relative to the same cross-section, but at a distance parameter of 0.4. And this value of 0.4 is chosen like this because this is the standard distance parameter of CMS during round 2. And then there are several comparisons to leading order and next leading order predictions, and as well with different Parton shower and non-perturbative corrections for each of them. So here, what we have in this figure in slide 5, on the y-axis is the cross-section ratio as a function of the jet PT for central jets. And each of these curves, the data points represented, and the different colors represent the scans for different values of R, and they are artificially displaced for visibility purposes. So from bottom to top, we have from the smallest J radius of 0.1 and up to 1.2. And here, what we see is that the slope in these cross-section ratios at low PT, it develops this slope at lower PT, and this effect is even more obvious when you go. Sorry? Sorry. So when you go to larger values of R, you're more sensitive to...
Is there somebody who is unmuted who should mute themselves, please?
Marek Karlinar should mute himself.
Okay, thank you. So when you go to larger values of the distance parameter R, you're more sensitive to these contributions from the underlying event activity. And then something else we note is that these cross-section ratios flatten more or less at a PT of 200 to 300 GeV. And here what we have in slide number 6 is again the cross-section ratio for a particular bin in PT as a function of the jet size. And the left-hand side is for central jets and the right-hand side is for forward jets. And so what we note here is that first from the data point of view is that this cross-section ratio generally increases as you increase the jet size. And the other thing to note is that among all of these different predictions, the best agreement is achieved at NLO for the general R parameter range, as you can see here in the ratio of the predictions to data. And however, when you go to the forward jet case, these NLO predictions generally overshoot the data as you go to larger values of R, as you can see in these data points over here. So this is the first study of its kind by the Siemens collaboration. Very interesting. And I'll move on now to the second study, which is related to angular momentum distributions in multi-jet production at 8 and 13 TeV. So here, the main interest of the study is to understand the regimes of validity between the matrix element approach and the Parton shower approach. And the main focus is on 3-jet production. And when you want to look at is at the delta R distribution between the second and the third jet, and the transverse momentum ratios between the third and the second jet. And so what you want to probe is the different regimes of soft and hard Parton radiation at small and large radiation. And here on the bottom is we see here all the details of the jet event selection criterion. So for the leading jet, it has a transverse momentum of at least 500 GeV. And the leading 2 jets are in central rapidities, whereas the third one is allowed to be within the full acceptance of CMS. And then to allow the trijet topology to occur, there's a requirement on the acouplanarity between the leading 2 jets as shown here. And then these last 2 selection requirements are related to the region of interest for this study. So what we have here is the normalized distributions as a function of the transverse momentum ratio. And the left-hand side is for the small angle emissions, and on the right-hand side is for wide angle emissions. And so what we see here is that the Pauheg prediction supplement with PTI supplementing the Parton shower and hadronization effects, and the PTI predictions are not able to describe data for small and wide angle emissions in these soft and hard regimes. And on the other hand, when you have MatGraph, which is for up to 4 partons at a matrix element level, this is able to describe this PT ratio spectra for wide angle emissions. However, it's not able to do the same for small angle emissions, for the left-hand side here. And then here, doing a similar exercise, but now looking at the delta R distribution between the second and the third jet, we have here on the left-hand side the event category when we look for soft splittings, let's say, so when this ratio is less than 0.3. And then on the right-hand side, we have when this PT ratio is larger than 0.6. So let's say for harder splittings. So in this case, we have that the NLO predictions with Pauheg give the best agreement in the delta R distributions for the soft and the hard PT regimes. And also just to mention that there is also results at 8 TeV, which are placed in the backup slides, but the results are very similar as in 13 TeV. So we find that there is no significant square root of S dependence on these 2 approaches for these observables. Now move on to the last measurement I'll be talking about, which is related to the production of 2 jets separated by a rapidity gap. And the main interest of studying this kind of events is that you are sensitive to hard color singlet exchange for these configurations. And in principle, you should be able to test the predictions based on perturbative QCD in the Balitsky-Fadin-Kuraev-Lipatov or BFKL evolution framework. in the high energy limit of QCD, and this will correspond to this two gluon ladder exchange in this limit. And this is related to the resummation of large logarithms of S and in particular to QCD. And then just to mention that since there's a central gap between the jets, the dynamics coming from declap evolution, on the other hand, will be strongly suppressed by means of a Sudakov form factor. So this is a very clean probe of VFKL dynamics. So these are, again, technical details about the event selection requirements for the study, which is based on low pileup data at 13 TeV. Using anti-KT jets with distance parameter of 0.4. The leading two jets have PT of a minimum PT of 40 GeV, and then you require them to be at a minimum pseudo rapidity of 1.4 units and to have opposite sign pseudo rapidities, basically to favor this T-channel color signal exchange. And then the central gap between the jets is defined as the absence of charged particle cracks between the jets, where the particle cracks have pseudo rapidities of -1 to 1 and a minimum transverse momentum of 200 MeV. So here, what we see here is the charged particle multiplicity distribution between the jets for a particular bin in PT of the subleading jet. And then what we see here is two ways of estimating the background contamination from standard dijet production, because they can still yield a pseudo rapidity gap by fluctuations in the particle multiplicity. The left-hand side is based on a data on an orthogonal dijet sample where the two are on the same sphere instead of on opposite spheres. The distribution from this control sample, and then you can see here that the predicted particle multiplicity counts at the lowest multiplicities has a different trend from what we observe in data for the sample of interest. So you see here this axis of events at lowest multiplicities. These are the hard color signal exchange signal events that we're interested in. And on the right-hand side, we do something similar, but with a negative binomial distribution function fit. And again, by doing the extrapolation to the lowest multiplicities, you see that there's an axis of events. So what we have here are the main results on this variable, which is the color singlet fraction. So basically the fraction of excess of events over background as a function of the of the pseudo rapidity difference between the leading two jets, the cell-beating jet transverse momentum, and the delta pi distribution, and the delta pi between the leading two jets. So, and what we have here are predictions based on the BFKL calculations and next to linear logarithm accuracy in the red line. And from this about the fields of the measurement simultaneously, which put very developed in the description of this kind of event. Jets are a crucial tool for understanding the comments that were reviewed in this presentation. The first one is related to inclusive jet cross-section as a function of R. The second one is on multi-jet production and the angular momentum correlation between the second and third jet. And the third one is on two jets separated by a rapidity gap to the B. And so thank you very much for your attention.
Thank you very much, Christian. I see one hand raised by Joy Houston. Go ahead.
Yes. So the measurement of the inclusive jet cross-section as a function of R is a very interesting measurement. There are next to leading order predictions that are available for this based upon literally on the CMS rivet routine for 8 TeV inclusive jet production. So if your binning is not so different from what was used at 8 TeV, and you have the non-perturbative predictions, which you seem to because you have them in accompanying the next to leading order predictions, you could do a direct comparison. And again, there the aim was to try to understand the R dependence of the cross-section at next to leading order, next to leading order, and then next to leading order plus parton shower.
Thank you. Yes, sorry, I missed. What was the question surrounding?
Oh, no, it was a comment just saying that you showed predictions up to next to leading order, and I'm just pointing out that the next to leading order predictions are available, you know, for these results are something very similar, since everything was matched to what was done in CMS at 8 TeV.
Okay, thank you very much. Yes. Yeah.
Okay, so I see somebody who is not muting himself. Miloslav, would you like to ask a question, or can you please mute yourself? Okay, I think we can move ahead to the next talk. Thank you very much, Christian. Our next speaker will be Camila Vittori on measurements of W and Z boson production in association with jets at Atlas.
Hello, can you see the slides?
Yes, thank you.
Okay. Good afternoon. I will present you the measurement of the WZ boson production in association with the jets performed by Atlas. These processes, the production of these processes is dominated by the strong interaction, and they allow to perform a precise test of perturbative QCD. So to taste the state of art of the actual predictions and next to leading order or next to next leading order, and for what concern heavy flavors, the difference between 4 and 5 flavor number scheme. Moreover, these processes are sensitive to C quark and gluon quark PDFs in proton and are background to X and U physics. So I will present you the most recent results that regard only the Z boson. So the Z plus jet production at 8 TeV and the Z plus B jet production at 13 TeV. Starting from the inclusive production at the 8 TeV, we measure the double differential cross-section as a function of the jet PT and rapidity at particle level, using about 20 inverse femtobar in the electron channel. As you can see from the plot that represents the distribution of the events as a function of the jet rapidity, this production is a very clean probe for QCD, and the dominant TT bar background, and the dominant background is the TT bar with a contribution of about 3%. The plot on the right is already a result, so it is the double differential cross-section as a function of the jet rapidity in the low PT bin of the jet, so between 25 and 50 GeV. The data are compared with several Monte Carlo simulations. As you can see in the first pad, of the plot, you have a comparison of data with the leading order Alpgen plus Pizia, which is in green, that agrees with data in this low PT bin, but then the agreement becomes worse at higher PT jet. Sherpa 1.4, which is in blue, underestimates the data of about 10%, but then the agreement improves at higher PT. And Sherpa 2.2, which is in orange, is in good agreement with data. Data are also compared with fixed order predictions. Like in red, we have the next to leading order MCFM, which underestimate the data of about 5–10%. And in magenta, we have the next to next leading order prediction, fixed order, which shows a better agreement with data. The measurements have been also compared with the fixed order prediction convoluted to with different PDF sets. So on the top, we have the plots where we compare the fixed order next to leading order MCFM prediction with the PDF 1614 with other two PDF sets, and the agreement is between 1 and 2%. And below, we convolute the next to next leading order prediction with two different PDF sets, which are CT14 and NPDF, and the agreement is between 2 and 5%. In general, the differences between the PDFs are covered by the theoretical uncertainties. Moving now to the measurement of the Z plus P jets at 13 TeV, we measure the inclusive cross-section and the differential cross-section, looking for processes with the Z produced in association with at least 1 and 2 B jets, using almost 36 inverse femtobar in the electron and in the muon channels. So we perform some kinematic reconstruction of the events. So we require specific cuts for the leptons, and then we require that the lepton belong to the Z boson. We apply kinematic cuts on the jets, and then we ask them to pass the B-tagging with an efficiency of 70%. Then, according to the number of B-jets in the final states, we divide the events in two categories: the one-tag region, where we have at least one B-jet, and the two-tag region, where we have at least two B-jets. The Z plus jet sample is modeled with Sherpa, which is 5 flavor number scheme next to leading order Monte Carlo generator as nominal. And then as an alternative, we use Alpgen, which is 4 flavor number scheme leading order Monte Carlo generator. Several processes are considered in the analysis, and you can see them listed on the top of the slide. The dominant background, the two dominant background are the dileptonic TT bar and the Z plus light or Z plus C jets. For what concerns the dileptonic TT bar, it is the dominant in the two-tag case with a contribution of 23%. To reduce it, we apply a cut on the ATMIS variable in the events where the PT of the Z boson is less than 150 GeV. And we validate the modeling on the TT bar in a region where we require opposite flavor, and we compare the data Monte Carlo agreement within the modeling systematics. The Z plus jet or Z plus C jet background is dominant in the one-tag signal region with a contribution of 36%. And to establish the correct contribution of this background, we apply a flavor fit. That is a maximum likelihood fit to data based on a flavor sensitive distribution. And this variable is the B-tag discriminant, whose example is in the plot on the right. So we take the shape of the Z plus B, Z plus C, and Z plus Liget from Monte Carlo, but we extract the normalization from the fit on data. So what we get from the fit are scale factors that are used to correct the normalization of the Z plus C and Z plus Liget background. In the plot, you see the distribution of the event as a function of the invariant mass, where the Z plus C jet and the Z plus Liget background have been scaled to their correct normalization. While for the signal, for the Z plus B jet signal, we use the prefit distribution. We combine the electron and the muon channels to increase the precision after verifying that the single lepton cross-section result were compatible within the statistical and the uncorrelated uncertainties. Then we extrapolate the measurement to the particle level. So we correct the data background subtracted distribution for the detector level effects. And we perform the measurement in the fiducial phase space defined by the cuts summarized in this table, which are very close to the detector level selection. To measure the differential cross-section, we perform an iterative Bayesian unfolding, while to measure the inclusive Z plus at least one and Z plus at least two B-jets cross-section, we correct for the reconstruction efficiency. The uncertainties, the uncertainties contribution to the measurements are summarized in this table. And we see that for the inclusive cross-section in the one B-tag case, we reach a precision of 10%, and in the two B-tag case, we reach a precision of 16%. The dominant uncertainty is the B-tagging efficiency. In the one B-tag case, one of the dominant is the Z plus Liget and C-jet background uncertainty that dominates in extreme phase space, as we can see from the plot on top that represents the breakdown of all the systematic contribution as a function of the ZPT. And we can see in magenta the contribution of the Z plus C and Z plus Liget background. Other sources of systematics are the top background and the unfolding method. Moving now to the results, our measurements are compared to several Monte Carlo predictions. So we compare leading versus next to leading order prediction and 4 versus 5 flavor number schemes. In general, if we look at the plots that represent the results for the inclusive cross-section, we see on the left, so for the 1B tag case, that the 4 flavor number scheme prediction, these 4, are all systematically lower than data. While the same prediction, these 4 flavor number scheme ones, are better in agreement with data in the plot on the right that concerns the 2B tag case. While in general, we can say that the 5 flavor number scheme prediction will describe both processes. Here I present you 2 plots as results for the differential Z plus at least 1 BZ cross-section. So differential cross-section on the left as a function of the ZPT and on the right as a function of the leading BZPT. For what concerns the ZPT, we see that all of the prediction show a trend at low value of the PT. The best agreement is given by Sherpa next to leading order, 5 flavor number scheme, which is the one in red. And the same behavior is confirmed by another version of Sherpa that combine the 4 and the 5 flavor number scheme, which is in magenta. If we look at the plot on the right, so at the leading BZPT, we see again that the best agreement is given by Sherpa 5 flavor number scheme, but this time the fusion version is not in agreement with data for high PT. And if we compare the results from 2 predictions of MATGRAPH, one is next to leading order and the other one is a leading order, which are both in light green, we see that the leading order one is better in agreement with data with respect to the next to leading order version. And this is due to the number of partons in the matrix element. Now I show you the results for the differential cross-section in the 2 tag region. On the left, you see the distribution as a function of the angular separation between the 2 BZs, which is a variable that is sensitive to the gluon splitting in BQuarks. This is the low range of this variable that is sensitive to this process. So we see that the Sherpa predictions, both in all of its versions, so 5 fusing and the 4 flavor number scheme, well described full distribution. And this is an improvement with respect to the run 1 results. On the right, you see the results as a function of the invariant mass of the 2 BZs. We see a good agreement for Sherpa for value less than 300 GV, but then we can see that none of the prediction well describe the data at high invariant mass. So concluding, I presented the most recent result of ATLAS for the V plus Z production. I presented first the Z plus Z cross-section at ATV, where we measure double differential cross-section as a function of Z variables. We compare the results with several Monte Carlo prediction, fixed order predictions, and PDF sets. And in general, we see that the uncertainty on the measurement are smaller or compatible with the theoretical ones. And this is a sign that the measurement can provide precision inputs for global PDF fit. And then I presented the inclusive and differential cross-section for the Z produced with at least 1 or 2 BZs at 13 TV. And the results are compared with the leading order versus next to leading order, 4 and 5 flavor number scheme predictions. In general, we see that the next to leading order 5 flavor number scheme Sherpa provides the best description of data, even if none of the several prediction that we test will describe the data for a large value of the invariant mass of the 2 BZs. In general, we can conclude that the measurements provide inputs for the improvement of theoretical prediction and Monte Carlo simulation, and can also improve our understanding of the perturbative QCD processes. Thank you.
Thank you very much, Camilla. Any questions for Camila, please? I see Anton Stepanov. Please go ahead.
I have a question about the selection and calculating the scale factors on slides 5 and 6.
Yes.
On slide 5, there is a step when you select B-jets using a B-tagger.
Yeah.
And on slide, and on the next slide, there is a step when you calculate the correction scale factors using the fit of the shape of B-tagging discriminant, right?
Yes.
So the question is whether these are the same discriminants, the same B-taggers which you use for selecting B-jets and for fitting of its shape to obtain the scale factors, or they are different?
Indeed, the variable that we use to perform the fit is the B-tagging discriminant, yes. But the B-tagging has an efficiency, so we want, and the B-tagging has an efficiency, yes. So we want to correct the shapes, yes, and the normalization of the B-tagging discriminant for the Z plus B, for the Z plus C and Z plus YZ background for their correct normalization. And we extract them from the fit on data.
And these are the same discriminants which were used to select the B-jets, right?
Yes.
Right, thank you.
It is binned in calibration bins. So the first bin, yes, each bin corresponds to 50%, 70%, and another one 77%.
See, thank you.
Thank you. Any more questions? I have very curiosity question, mostly because I don't know exactly the details that go into the Monte Carlos. And maybe it's a question to Frank Ziegert than you. So what happens in the fusion version where you have both 4 flavors and 5 flavor scheme incorporated at NLO? I mean,
so maybe I can try to answer it,
yeah, exactly.
if you want.
Yeah.
So basically, you try to identify in the fully showered final state, based on the clustered history of that fully showered final state, whether you have a dominantly ZBB-like configuration or you have a Z plus jets configuration with with softer B jets. And depending on what kind of configuration is, you take it from a ZBB 4-flavor scheme-like simulation or from a Z plus jets merged NLO calculation. So this is a very rough idea of it.
Okay.
Because there are lots of details which you have to make sure to match the 4-flavor and 5-flavor scheme variables, like using 5-flavor scheme PDFs, but using a massive B quark in the virtual corrections. You have of course matching. You have to match coefficients which correct that you have a mismatch between those. But those are all the details. But the main idea is to really try to identify which of the 2 setups is better suited to describe the kind of configuration that you have on an event-by-event level, and then take it from the corresponding simulation.
Thank you, Frank. Because I find it interesting that the 5-flavor scheme seems to give a better agreement with data so far. So I know this simplifies life, because then, you know, it's 5-flavor scheme, I stick to it. And I think even for you guys, it's simple to kind of just implement. Anyway, so thank you very much. And I think we need to move to the next talk by Anton Stepanov. So thank you, Camila. And so the talk will be on vector boson plus heavy flavor jets and constraints to PDFs in CMS. Please go ahead.
Good day, everyone. On behalf of CMS collaboration, I want to show you the results of studying events with WZ boson with heavy flavor jets. And I'll start with motivation. First, studying such events can be a good test for existing theoretical models and event generators, which could have been tuned to better describe V plus jets without discriminating the jet's flavor. The second is the search for the new physics, where events with heavy gauge boson and heavy flavored jets can be a background. For example, in the search for third generation squarks, the final state contains 2 charm quarks and 2 light SUSY particles, which are unidentified. And for example, the events like Z plus charm jets can mimic such final state when the Z decays invisibly into two neutrinos. And finally, such processes can be sensitive to the PDF of strange charm or bottom quarks. And the examples of the diagrams which correspond to such processes are shown here. This table shows a short summary of the recent results which I'm going to show you today. But before going into details, I want to show you a short overview of the methods which were used to identify the presence of heavy flavor quarks in the event. There are three options. The first one is to reconstruct D or D star mesons by selecting tracks, assigning pions and kaons to these tracks, and reconstructing the decay chain of D or D star meson. The plot, this plot shows the distribution of mass difference between reconstructed D star candidate and D0 candidate. And as we can see, the D star candidates from W plus charm events tend to be in a very narrow peak. The second option is to select jets with a muon inside them, which originates from decay of a charged hadron. And the example of such muon PT distribution inside the jet is shown on this plot. And as we can see, for the events with Z boson and jet, most of the events are from charm or bottom components. And the third option is to select various variables which are associated with the jet. For example, mass of secondary vertex or the distance between secondary vertex and primary vertex, which allow to discriminate signal from background. And one can also create a dedicated C or B tagger, which uses all these variables and creates a discriminant which separates one particular flavor from light jets and other flavor. Now let's move to the W plus charm study at 13 TeV. In this analysis, charm quarks, the presence of charm quarks were identified by the decay products of D star using the following decay chain, so that in the final state there are two pions, one with small pt and one kaon. W bosons were identified by requiring one muon with the following kinematic cuts and transverse momenta higher than 50 GeV. And also, after making the selections, the events with W bosons and D star candidates with the same flavor were subtracted to take into account gluon splitting. On the right, there is a short summary of integral fiducial cross sections and the ratio of total fiducial cross sections for W bosons with different sign. Also, differential cross section is a function of the rapidity of muons were measured for the cross section of W plus charm quark and for the cross section W plus D star meson. And in both cases, we see a good agreement between theoretical predictions and data. This process is also sensitive to PDF of strange quark and strange suppression factor. So the top two plots show the results of measuring of strange quark distribution, and two bottom plots show the results of measurement of strange suppression factors and comparison it with MBMP results and Atlas results. And as you can see, there is a good agreement between this analysis results and MBMP results. However, these results do not support the results from Atlas. However, one should keep in mind that Atlas results were obtained using next to leading order, while MBMP and this analysis results were obtained using next to leading order. This analysis was also done at using ATV data, and the selection for W boson is similar to the previous analysis, except that both muons and electrons from the decay of W bosons were taken into consideration. The chunk work present, however, was done in two different ways. The first is the selecting of jets with the reconstructed muon inside them with falling kinematic cuts. And the second option was to select jets with reconstructed secondary vertex mass with reconstructed secondary vertex with a mass higher than 0.5 GeV. So after this was done, both integral fiducial cross sections were measured and differential cross section values as a function of pure rapidity of the selected lepton or PT of the selected lepton. And as we can see, there is the results of the measurement and theoretical predictions are consistent, though theoretical predictions tend to slightly underestimate the data. This analysis also allowed to measure the difference between cross sections for different signs of W boson, both for integral fiducial cross section and differential cross section values. Now we're moving to analysis with Z plus heavy flavored jets, and the first one is Z plus charm jets at 13 TeV. In order to select Z boson, we required two opposite sign leptons, muons, or electrons with the following kinematic cuts. And to identify the presence of the jets initiated by chunk work, we required the jets to pass C-tagging criteria. This is the output of the neural network, which uses different variables associated with the jet, which allows to discriminate jets initiated from the chunk work from the jets initiated by bottom and light works. And after selecting events this way, the number of Z plus charm events was calculated using secondary vertex. On this plot, the distribution of secondary vertex mass for various flavors is shown, and doing the fit of light charm and bottom components to the data, the number of Z plus charm events along with the correction factors for light charm and bottom components was found. And in order to validate this method, these correction scale factors were applied to the corresponding flavor components in Monte Carlo. And this plot shows the distribution of Z transverse momentous spectra after applying these correction factors to the corresponding flavor components. And as we can see, there is a good agreement between data and Monte Carlo after this procedure. So after the number of events, Z plus charm events was measured in different Z or CJet PT bins, the resulted distributions were unfolded so that it was possible to compare the results with different theoretical predictions and predictions of different Monte Carlo generators. These are the results of the unfolding. The plot on the left shows the differential cross section as a function of PT of the CJet, and the plot on the right shows a differential cross section as a function of PT of the Z boson. We also compare the results with the predictions of different Monte Carlo generators. The green one shows MET graph next to leading order predictions with QCD and PDF uncertainty band. The blue one shows MET graph leading order, and the red one shows sharp predictions. And as we can see, the predictions of MET graph leading order are consistent with the predictions with the measurement. However, the predictions of Sherpa and MET graph next to leading order overestimate the data in all bins. And the final result I want to show you today is the measurement of the ratios of Z plus charm and Z plus bottom cross sections. For this analysis, the selection of the Z boson is similar to the selection of the Z boson from previous analysis. However, in order to select events enriched with heavy flavored jets, B tagging was applied instead of C tagging. After selecting of the events this way, the number of Z plus charm and Z plus bottom events was found through the fit of the shape of secondary vertex mass. And this plot shows secondary vertex mass distribution after charm and bottom components were fitted to the data. And for variation of the modeling of second vertex mass by Monte Carlo, the distribution of second vertex mass in data for TT bar events was compared with Monte Carlo predictions for Z plus bottom jets for the same value. And as we can see, there's a good agreement between data and Monte Carlo, thus this variable can be used in the fit. And after these procedures were done, the ratios of cross sections for various flavors as a function of PT of the jet or PT of the Z boson were done. And we see that there's some disagreement between the measurement and the prediction of both mid-graph leading and next to leading order and MCFM for the ratios of Z plus bottom jets and Z plus all jets, Z plus charm jets and Z plus all jets, and the ratios of differential cross sections for charm and bottom components. And this brings me to the summary. Different studies of events with Z or W boson with heavy flavored jets was done by CMS using run 1 or run 2 data. We see that there is some disagreement between the measurement results and predictions of different models and Monte Carlo generators. And thus there's still room for tuning those models. The strange suppression factor and PDF of strange quark were updated. And finally, and most important, there are more works of VP plus heavy flavored jets upcoming. That's all. Thank you very much for your attention.
Thank you very much, Anton. And I think we have a question from Mandy. Please go ahead.
It's actually a comment on slide 6. And it's just to say concerning the comparison of the strangeness suppression factor to the Atlas result, that it's somewhat misleading as presented, not just because it's NNLO instead of NLO, but because what is shown there in the green band is only the pure experimental uncertainties from the Atlas PDF, when we also produce model and parameterization uncertainties, which makes our uncertainties quite a bit larger at the high X end. So whereas there is a remaining discrepancy around X of 10 to the minus 2, you really won't find it to any extent at 10 to the minus 1 if those extra uncertainties were added. And we have asked the CMS management to do this several times already, but I'm disappointed to see that it's still the same plot that I saw last year. Anyway, that's the comment.
I see. So if I understood you correctly, the error bands for Atlas results should be different in this comparison, right?
They should be somewhat larger, but more particularly so at high X.
I see. Thank you.
Okay.
We have one more question from Zurak.
Yes, thank you. I wanted to ask you, because this reaction, this fast reaction you discussed, in principle can be used to look at asymmetric strange C. So first, my question is, in your calculation, I understand C is assumed to be symmetric, S equal to S bar. But in principle, this data could be used to extract asymmetry of the strangeness. So can you comment on this?
I'm not sure whether the authors wanted to have an idea to measure this asymmetry for this particular analysis. But yes, perhaps this can be done using this data.
Thank you.
Okay, someone else has unmuted themselves, so please mute yourself unless you're asking a question. There is a sound in the background.
Yeah, of course.
Okay. All right, so I think we can move on to the next talk. Thank you very much, Anton. So the next talk will be by Mariana Mazzilli on heavy flavor correlations, jets, and multiplicity-dependent studies on heavy flavor hadrons in small systems with Alice.
Can you hear me?
Yes.
Okay. So, can you see my slides?
Not yet. We see black screen.
Okay.
Yes, now we can see you.
Okay. So, good afternoon to everyone. Today, I'm going to present a selection of results about the heavy flavor jet correlation and multiplicity-dependent heavy flavor hadron measurement made with the ALICE experiment in small systems. So let me start with the physics motivation. We know that heavy flavors, so charm and beauty quark, are produced in the earth scattering processes, and their study in proton-proton collision led us to provide an important test of our current understanding of the perturbative QCD, and they of course represent a mandatory reference for more complex systems such as proton-lead and lead-lead collision. In proton-lead collision, we would like to investigate for the so-called cold nuclear matter effects, so those effects that arise from the presence of a nucleus in the collision. And in particular, since we already observed similar collective features of those observed in lead-lead collision as the non-zero V2 or the double fidge of long-range correlations, we would like to further investigate for possible collective effects. Then in particular, related to the main topics that I'm presenting today, we know that heavy flavor and correlation give us a more differential characterization of the heavy quark production, fragmentation, and hadronization processes in comparison, for example, to single particle measurement. They indeed give the possibility to access directly to the initial parton dynamics. In addition, complementary studies have been carried out with the heavy flavor correlation, which led us to access directly to a detailed characterization of the charm-induced jet. For what concerns the multiplicity dependence of heavy flavor studies, here we have the chance to investigate for processes at the parton level, as well as the interplay of soft and hard mechanisms. And they represent also a good observable related to the underlying event associated with heavy flavor production in proton-proton collision. So in the measurement presented in this talk, I will, many of the ALICE detector have been used. In particular, the tracking and the vertexing detectors allow for the reconstruction of the jets at very low PT, and also for the reconstruction of secondary vertexes that are essential for heavy flavor measurement. Then several detectors provide the different triggers, such as the V0 and the SPD for both the minimum bias and the high multiplicity triggers at different rapidity region. Then we have also the muon trigger, which is provided by the muon spectrometer for the forward rapidity measurement. ALICE then is also able to identify charged particle by means of different techniques. For example, the specific energy loss is employed by the time projection chamber and the time of flight by the multi-gap resistive chambers of the time of flight. And we have also the identification of mid and high PT electrons through the E over P ratio with the chemical detector. So let me start with the heavy flavor jets and correlation, in particular with the heavy flavor electron jets. Here, in this analysis, the jets are identified by the presence of an heavy flavor decay electron. So an electron which basically comes from the semi-leptonic decay channels of B and D mesons. Here the jets are reconstructed by means of the anti-KT algorithm, which favors the clustering of IPT particles with small angular separation. And the reconstruction is track-based in the sense that the jets are reconstructed with only their charged particle constituents. Here you can see the PT differential cross-section of jets identified by the presence of heavy flavor electron in proton-proton and in proton-lead collision, both at 5 TeV. The results here are compared with the POVEG expectation. POVEG is a next leading order Monte Carlo generator, which basically is then combined, which reproduce the initial parton scattering, and the parton shower and the hadronization processes are then performed by means of PTI8. As you can see, there is a good agreement among data and theory prediction, as you can see also in these bottom panels where the ratio among data and theory is reported. Then, in order to further investigate for possible final state effects in proton-lead collision, the production of heavy flavor electron jets has been measured with different resolution parameters that reflect in some way the modification of the jet shape and the particle transverse momentum composition within the jet itself. In general, we know that the modification of production yield in proton-lead collision with respect to proton-proton collision is quantified by the nuclear modification factor, which is defined as the ratio of the PT differential cross-section in proton-lead collision with respect to the proton-proton one scaled by the mass number A. Then, if there are final state effects, we would expect that the RP-lead should be minor than 1. Here, the R dependence of the RP-lead is reported, and it is consistent with the unity over the whole PT range. These results indicate that there is no significant modification of the heavy flavor production due to final state effects, as well as initial state ones. Then further study are also of the modification of jet from heavy flavor can be performed by calculating the ratio of cross-section with different R. In particular, in case of final state effects, we know that heavy quark lose energy and jet shape is expected to be broader and the radial profile of jet should be modified. To this purpose, we measured the ratio of cross-section, which is sensitive to this kind of a modification. So the reference cross-section is the jet measured with the R equal to 0.3, and the ratio is calculated with respect to R equal to 0.6 in both PP and P-lead collision. Within uncertainties, the cross-section ratios in PP and P-lead are consistent, and they show to be consistent also with the theory prediction, making this exception just for this last pin, which is however affected by larger uncertainties. The agreement suggests that POVEG expectations describe not only the production yield, but also the shower development in radius of heavy flavors. Now, let me move to the zero-target charge jets. Here, the jets are identified by the presence of the zero mesons reconstructed in their hadronic decay channel K-pi. And for the jet reconstruction, here again, only charged particles enter in the track-based reconstruction of the jet. The clustering of tracks is performed using the anti-KT algorithm. And here you can see the PT differential cross-section in PP collision at 5 and at 13 TeV. An overall agreement with theory prediction at next to leading order is found also here, even if, let's say, an increasing difference between data and theory is found for decreasing PT of the jet. Now, in order to further investigate the heavy quark fragmentation, a relevant observable was introduced, that is Z parallel, which is the fraction of the momentum carried by the heavy flavor hadron in the direction of the jet. In this slide, you can see the probability density of the Z for two different PT intervals of the D0 jet. So here for 5 to 7 GV/c, and here from 10 to 15 GV/c. At lower PT, the interval, the distribution peaks at 1, and this case corresponds to jets with only the D0 meson as jet component. The comparison with POVEG here is good at higher PT, while it exhibits some tensions for the lower PT range of the jet. Analogous measurements have been performed also for G0 jet at 13 TeV and lambda C jet at 13 TeV. And let's say we can here make analogous observation with respect to those made in the previous slide. And so both for D0 and lambda C, we can say that in general, the comparison with models point towards a softer fragmentation at lower PT jet in data. This measurement, let's say, in particular related to the fragmentation function, are open the possibility also to compare baryon and meson fragmentation function that is now an important field under study. So the study of angular correlation distribution of the meson with charged particle allow for a more detailed characterization of charm-induced jet. In particular, we know that the typical angular correlation function features a near side peak in delta phi equal to 0 and an away side peak in delta phi equal to pi. In particular, the near side peak allows for to probe in some way the spatial profile and the charm jet particle multiplicity. A more quantitative investigation from this side can be performed by quantifying, for example, the peak yields and widths extracted from the fit to the correlation function as it is shown in this plot. The values of the observable here are when extracting the yields and the widths, in this case for both proton-proton lead collision, we can see that the observables are fully compatible among the two collision systems. In particular, you can see this increase of the associated charged particle inside the near side peak for all the associated PT of the associated particles. And it appears to be, let's say, compatible among the two collision systems. For what concerns the angular profile, you see that the near side peak have this tendency of collimation for increasing the PT of the dimension. Then, let's say, given the compatibility that we are observing among the near side observables in the two collision systems, we would conclude that within the current uncertainties, there is no sensitivity to observe co-nuclear matter effects in this case. Now, comparing the proton-proton yields and widths with models, which are characterized by different treatment of the arc scattering process, the parton shower, and subsequent hadronization, we can say that we found, let's say, that all the models provide a fair description of the near side correlation peak. And in particular, we can say that the two models that seems to catch better the data, as you can see, especially here in this ratio, provided among the yields and Povec plus PITIA 6 event generator, you see that Povec plus PITIA is the closer to unity. And so it's the model that maybe provides the best description of data together with PTI 8. Then we have that Ervig, for example, tends to underestimate near side peak yield for especially for PT of the associated tracks larger than 1 GeV/c. And for EPOS 3, we can see that there is this systematically overestimate the near side peak. Okay, so let me move to multiplicity dependent Lefleur Hadron measurement. So here as a first study on this topic, I reported the JIP psi production in proton-proton collision at 30 TeV. Here, the JIP psi is measured at mid rapidity in its dielectron channel, while the charge particle multiplicity is evaluated at mid rapidity with the SPD event selection and at forward rapidity with the DV0 event selection. Here, both observables are then normalized to their corresponding average in the minimum bias event. So what we can see is that the measurement show to be, so first of all, we can see that the normalized GPSI yield grows faster than linear with the normalized multiplicity. And when compared SPD and V0 event selection, these are found to be in agreement. And in particular, the V0 event selection removes the possibility of an autocorrelation bias in the mid-rapidity regions with the SPD. Going differential in PT, the data show a significant increase of normalized GPSI yield in 0 to 4 and 4 to 8. And this effect, let's say, could derive from several contributions. So for example, from the associated GPSI production with other hadrons in the jet fragmentation, or from the beauty fragmentation that, since we know that, for example, the feed-down component increases with the PT. Oh, here you can see also the comparison with several theoretical models of the GPSI normalized yield with respect to the charged particle multiplicity yield. And in particular, all these models actually are able to reproduce this increasing trend by implementing different physics mechanisms actually. In particular, to evaluate also, for example, the effect of non-prompt GPSI. In this case, we considered only prompt GPSI in PYTHIA. And as it is shown, we have a significant reduction of the correlation in this case, which appears, however, to be stronger for the SPD event selection. In this case, for example, PYTHIA implements multiple parton interaction in order to reproduce this increasing trend of data. So, okay. Now, when looking at the normalizing yields of GPSI reconstructed this time in the dimuon channel as a function of the charged particle multiplicity density, we found this time a linear increase. So different trend that we are observing among mid-rapidity and forward rapidity. Actually, it's something that it's not due to possible autocorrelation as we saw in the previous slide, but actually it points toward different mechanisms, which is at the moment still not fully understood. In this same plot, you see also the bottomonium, which is so the upsilon1s and the upsilon2s as a function of the charged particle multiplicity. And it shows this linear increase this time. That is also the trend that was found also for the Psi2s. So now another interesting measurement is this relative production of, let's say, this weakly bound quarkonium with respect to the stronger bound quarkonium. So for example, here you see the Psi2s over the JPSI normalized relative production. And what we see is that let's say this ratio is compatible with unity within 2.2 sigma in this first bin. And but actually this is also this tends to point towards a suppression of the Psi2s with respect to the JPSI, which is also reproduced by models implementing final state effects, even if the model, let's say, foresees a stronger suppression for large multiplicities. In particular, charmonium and bottomonium relative production ratios seems to be in agreement with among themselves. Now, moving to the proton lead measurement, we can see that here the JPSI is reconstructed at backward and forward rapidity as a function of the normalized charged particle multiplicity. In particular, the yield at backward rapidity, so in the left-going direction, grows faster than linear, reaching values above those expected from a linear increase at large multiplicities, while when going at forward rapidity, so in the proton going direction, the values show a slower than linear increase at large multiplicities. Here, the measured yield in proton lead are compared with the EPOS3 event generator expectations. And here EPOS3 is considered in both hypotheses with Hadron and without hydrodynamic evolution. Let's say that in this case, the number of simulated events, especially at large multiplicity, is limited and does not allow to elucidate for possible hydro effects. Then the average transverse momentum has also been measured, and it shows to be smaller at backward than at forward rapidity, consistent with the decrease of the average PT, so the softening of the spectra that we expect with the increasing rapidity of the center of mass. In particular, we see that the average PT increases steadily for multiplicity below the average and saturates above the average multiplicity. And let's say these two features can point toward a GPSI production from an incoherent superposition of parton-parton collisions. So in the end, here I show the normalized yield of heavy flavor decay electrons as a function of the normalized charged particle multiplicity at mid rapidity in PP collision 30 dV and also in PLED collisions. And what we can see is that here at higher PT intervals, we have a hint of steeper increase of the normalized yield. In particular, we found also a good agreement with PTI8, with the PTI8 predictions. As I already said before, PTI8 implements multiple parton interaction in order to reproduce this increasing trend. So this brings me to the conclusion. And I presented you the heavy flavor jet and correlation. And in particular, we found that in general, we have a good agreement with theory calculation at next to leading order accuracy, especially at type PT of the jet. For both lambda C and zero fragmentation function measurement, we found that data point toward a softer fragmentation at lower PT of the jet. When investigating for nuclear matter effects or final state effects, we did not observe any evidence within the current systematic and statistical uncertainties. While for what concerns the multiplicity dependent studies, I've presented the normalized yield of heavy flavor electrons of all quarkonia. And what we observed is in general a rapidity dependence of the yield in proton-proton collision. In proton-lead collision, we saw a different trend at backward and forward rapidity, which basically derive from nuclear matter effects. While in general, we can see that the theory models, even if implementing different physics mechanisms, are able to reproduce the trend of data points. And let's say we look forward for new and more precise measurement with RAM3. Thank you.
Thank you very much, Mariana. Any questions for the speaker? Okay, I don't see any raised hands, so I think we can move on to the next talk.
Sorry, I had one question.
Okay, Sue Zurak, now I see your hand. Yes, please go ahead.
Sorry. Yeah, I have some doubts on your conclusion 3 because I think it may be more complicated. You are writing no evidence for cold nuclear matter effects because we know that in proton-proton collision we have gigantic contribution from multi-parton interactions. So this nuclear modification factor, and we know that this multiple interaction in PA collision would be bigger than in PP collisions. So in principle, looking at this, there should be enhancement of the cross section. However, we see about unity. So perhaps there are two canceling effects. I mean, this nuclear, I just want to note that this nuclear modification factor is defined, makes sense, provided the dominant processes are single parton scattering. But if there's multiple parton scattering, I think it could break in principle. I didn't see study, but this is I want to make such a remark that one should be a little bit careful whether we see.
Yeah. But indeed, actually, this was something related, especially with this observation, so related to the study of the Hadron correlation that I reported. Indeed, yes. We know that there are cold nuclear matter effects. I mean, and what I was saying is just that within the current uncertainty, we cannot claim here, for example, for the presence of cold nuclear matter effects. And actually is also what we see when we compute here the nuclear modification factor for the heavy flavor electron jet, since we see that in case we are affected by cold nuclear matter effects, actually the nuclear modification factor investigates more final state effects which are related with, for example, with the presence of core gluon plasma. But in any case, this could also be affected by the presence of cold nuclear matter effects. But since we see that here this is compatible with unity, of course, this takes into account that we are, let's say, in proton-lead collision, we have the nucleus, so the proton-proton collision cross-section is scaled by the mass number. So, I mean, these were already taken into account in our measurement.
Thank you very much.
You're welcome.
Thank you, Mariana. Any more questions? I'm not seeing any raised hands. So if this is the case, I think we can move on to the next talk by Amanda Serkar on HERA jet data in NNLO fits of HERA PDF and diffractive PDFs.
Hello. All right, can you see this?
But not in the full screen mode.
Yeah, I'll just put it in full screen mode. Give me a minute. I just need to get rid of something else off the page. Yeah, okay. Okay, right. So I want to report on two different analyses which have been enabled by the fact that we now have next to leading order predictions for jet production. The first is the updating of the HERA PDF 2.0 jet fit at NLO to NNLO using the predictions from the NNLO jet group as implemented in the AppleFast system. And the second is an update of the H1 analysis on the diffractive PDFs, also to NNLO using the predictions for jet production. So beginning with the HERA PDF, at the time of the publication of these PDFs at LO, NLO, NNLO, NNLO predictions were not actually available for the jets. So we've revisited this, and indeed in the interim also some more jet data has become available. So we've used the same data sets we used in the previous published analysis, but we've added new ones as indicated on this table. However, there are a few caveats to that. At that time of the NLO analysis, we had tri-jet data, which does not have the NNLO prediction, so those are not included. And we've had to make somewhat more severe cuts on the PT squared plus Q squared of the data in order to have reliable NNLO predictions. Okay, so there is, when you're dealing with jets, there's always a choice of scale. And previously we had used the factorization scale as just the scale Q squared. This is really not a good choice for low Q squared jets, of which we now have many more because of the new data set. So we're now using Q squared plus PT squared for all the jets. And we're using the same scale, in fact, for the renormalization scale in this analysis. It seems, at least at NNLO, to be a better choice of scale than our previous choice of half that quantity. And it does seem that the optimal scale choice at next to leading and next to leading order is actually different if you, at any rate, if optimal is to some extent defined by that which gives you the lower chi-squared. We do, of course, investigate the consequences of scale variation. Now, the HERA PDF, just as a brief reminder, is based on the combination of the final HERA run 1 and run 2 data, and it supersedes the previous HERA 1 combination. And the HERA 2 jet fits simply add HERA jet data to that, as well as analyzing the PDFs with experimental uncertainties by the Hessian method. We also in HERA PDF have also given you model assumptions from the variation of assumptions as to what is the charm mass, say, the beauty mass, the minimum Q squared of data entering the fit, the strangeness fraction, and also variation of our parameterization. We have a simple polynomial parameterization, but we consider adding further terms to it in order to consider parameterization uncertainty. And indeed, a variation of the starting scale for evolution. When you're including jets, you also have to evaluate the hadronization uncertainty, and that we do by offsetting the corrections that are given for each individual jet data set. So the standard value that we put for alpha S in HERA PDF fits, it comes from the PDG as 0.118. But when you have jet data, you can also make an evaluation of alpha S by performing simultaneous fits for the PDF parameters and the parameter alpha S. And we did that for this NNLO jet analysis. And you can see in the plot the shape of the curve of the chi-squared against the value of alpha S, which is now giving us a value, in fact, written on the bottom of the slide as 0.115. In addition to evaluating the experimental uncertainties, we add the model and parameterization uncertainties that I was just mentioning to this, and the hadronization uncertainties, and also the scale uncertainty. So the scale uncertainty is determined as usual by changing the factorization and renormalization scales by a factor of 2 in the usual 7-point variation and taking the maximal positive and negative deviations. But the procedure that we had applied at NLO and is now applied again at NNLO is that we consider these deviations as 50% totally correlated and 50% uncorrelated. So that's how the scale uncertainty was evaluated. And as you can see, it's the largest error on alpha S. Just to put this in context, I've put again a plot which comes from the old original HERA PDF analysis of scans of the chi-squared against alpha S. First of all, at NLO, where you can see a fit which includes charm and jet data scan on the top, and underneath it, what you get if you only include inclusive data. So you can see that inclusive data alone are just not able to give you a reasonable evaluation of alpha S. At the time when this older paper was published, we only had predictions for inclusive at NNLO. So we had the third plot down, and we're now adding to that the plot from the present analysis. I've just scaled it to look on a similar scale to the other 3 below. So you can see that the value of alpha S at NNLO is considerably lower than that at NLO. And in fact, although I mentioned earlier we were using a different scale choice before, in fact, if we had used the same scale, the difference would only be larger. It would move our current result even lower to 1135. So on the end of that slide, there is a summary of the present NNLO result with all its various error contributions in red. And then underneath it in blue, the previous NLO result. And the main thing to note on this is that the scale uncertainty is reduced going from NLO to NNLO. Now, just to look at the PDFs that are extracted by this process as well, we're comparing on this slide the PDFs both evaluated at with alpha S 0.118. One of them is the original inclusive PDF at NNLO, and the other is the new JETS fit that we're presenting today at NNLO. And the new one is in blue, the old one in red. You can see this compared for U valence, D valence, gluon, and the total C. And really the place where you'll see the main difference is in the gluon itself at low X, which is a little bit shifted and a little bit reduced in uncertainty. So on the next slide, I'm just comparing just two examples here of Zeus inclusive jets on the top and H1 normalized inclusive low Q squared jets on the bottom, just to show you the quality of the fit to the data points. And there are many more comparisons in the preliminary publications that go with this of how well this fits the data. So that's finished for looking at the update to the HERA PDF. Now we consider an H1 analysis of diffractive production in EP, and just in case not everybody is as familiar with this as they are with the inclusive PDFs, the real idea here is that you're looking at a process with a large rapidity gap where you're assuming that what's actually happening is that the proton is very little disturbed and it's exchanging a colorless exchange, giving you a large rapidity gap before it's then affected by the incoming photon probe. So you've got a fractional amount of momentum going into the, well, what we'll call the pomeron, the colorless exchange. And then you've got a further fraction of that, that's X sub P. And then the further fraction of that is called beta, how much of the momentum of the pomeron is actually involved in the struck quark. So what we're trying to do is determine the parton distribution functions of the colorless exchange, rather than our previous attempts to determine the PDFs of the proton. So the data that are fitted are inclusive diffractive data and diffractively produced dye-jet data. And the reason for this update right now is that there is now 40 times higher luminosity in the inclusive diffractive data and 6 times higher luminosity for the diffractive dye-jet data than there was at the time when the previous analyses for diffractive PDFs were done. So on this page, I briefly summarized the publications from which the data are coming. One of them was already a combined data with large rapidity gap, which is somewhat expanded out in the middle table. So the first two tables are of inclusive data, and the one on the bottom of the slide is the details of the dye-jet data that have been included for this fit. And the way that you do this is you have to consider the process such that you've got a convolution of the pomeron flux and the PDFs in the pomeron. So the pomeron flux is F of pomeron sub P, and its PDFs are F sub I pomeron. And you also have a similar term for any Reggie exchanges, which don't make a big contribution, only a few %, but need to be accounted for in the formalism. The table is giving you what were the parameterizations for the gluon and the singlet in the pomeron for previous H1 diffractive fits, and also for the present fit. For the region exchange, in fact, one is just assuming that the region PDFs would be similar to that of the pion PDF. And only the overall normalization there is taken as a free parameter. So on the next slide, I am summarizing what the parameters are. Some of them are fixed from previous data and some are free. So the first equation gives you the form of the pomeron flux in terms of the region intercept and slope. And we in fact consider the data integrated over the momentum exchange at the pomeron vertex T, so that this simplifies to the second expression. And we are fitting the pomeron slope, but fitting the Pomeroy intercept, but fixing the Pomeroy slope. And the table gives the details of which parameters are, what values they're taken from previous publications on diffractive data. So finally, what you've got for the fitted parameters are 6 parameters from the Pomeroy PDF itself, a parameter for the Pomeroy intercept, and a parameter for the normalization of the Reggie exchange. And this is fitted, and then the scale variations are also varied up and down by a factor of 2 in order to get the total uncertainties. So on the next slide, I show you the PDFs, the shape of them for the singlet and the gluon at 3 different scales, at a low starting scale 1.75 GeV squared, at 20 GeV squared, and at 800. And you can see the differing shapes of the singlet and the gluon evolving. Now, the new fit in blue with its full uncertainties in pink, so theory uncertainties essentially means both the variation of the scale and the variation of the parameters that I gave on the previous page within their uncertainties. And this is compared to the previous diffractive fit in pink, noting that the previous fit was an NLO fit, not an NNLO fit. And the main result that you can see from that is that the gluon diffractive PDF is considerably reduced at NNLO. Nevertheless, it's still true, as is usually found in diffractive fits, that the gluon is much more prominent. It's the dominant PDF, even up to quite high values of momentum fraction. To show the quality of the fit to data on this slide, the inclusive diffractive data are shown as functions of the submomentum fraction beta and the scale q squared, all for fixed values of the momentum fraction of the Pomeroy. And you can see a very good quality of the fit to both those quantities on this slide. And then for the dijet data, the double differential dijet data that are put in the fit as functions of PT in slices of q squared, this slide is showing you the quality of the PDF fit for those data. Now, those are the dijet data that were actually input to the fit, but the following slide also shows you what predictions this fit gives for other classes of diffractive dijet data that are not put into the fit. And you can see that in each case, for the kind of, it's listed on the bottom on the x-axis that H1 data from the forward proton spectrometer, very forward proton spectrometer, large rapidity gap events at HERA1, HERA2, and so on, that all these classes of data are very nicely described by the NNLO fit. And you can also see that the previous fits at NLO could never do so well. They were over predicting these jet cross sections. Okay, so in summary, the 2 analyses shown, one is the completion of the HERA PDF, including next to leading order predictions for the jet data, and resulting in 2 new PDF sets. We will be issuing these new PDFs at both alpha S 0.118 and 115. And the reason to do that is because the NNLO data would seem to prefer the lower value. So we have a new preliminary evaluation of alpha S from this analysis compared to the previous result. So there's a shift down in the value of alpha S and a reduction of the scale uncertainties. And then the second analysis is showing diffractive parton distributions extracted at next to leading order for the first time. They have a lower gluon compared to the next to leading order analysis, and the jet data are now very well fitted together with the inclusive data, with very successful predictions for the HERA diffractive jet cross sections. So that's it. Thanks.
Thank you very much. Are there any questions for Amanda?
Yes.
I see one from Marek Karliner. Go ahead.
Yes. In the plots, you have shown comparison with mostly H1 data. How does it compare with the Zeus data?
Okay, good question. The reason that I've done that is because this diffractive analysis that I'm showing now was an H1 analysis. So within the context of the paper and the plots that I have, I only had H1 to compare to. So I can't answer your question at the moment. I think we should go away and take a look at that.
I see. And one other question is the difference between your fit value of alpha S as 115 versus the PDF value of 118 should be attributed mostly to scale uncertainty?
Well, yeah, within the scale uncertainties, it is still compatible.
Yeah,
all I'm noting is that using very strongly overlapping data set and analyzing it both at NLO and NNLO, you can see a definite shift down.
Okay, thank you.
Any more questions? It looks like there are no more questions. And since we are already 10 minutes late, I think we should end this session. We will have 10 minutes break, and please feel free to use Mattermost to chat with the speakers to ask your questions. And we will rejoin again in 10 minutes from now. So in 10 minutes. For me, it's 10:40. So in 10:50 my time, I don't know what it is now in Europe, sorry.
41, this is 41 past 5.
Okay. So. Good, thank you, Laura.
Bye-bye.
Bye-bye.
Just a small comment. Speakers of the next part are free to test their setup, that they can share the screen.
Oh, I'd quite like to do that. This is Claire. Hi, if possible, just because I noticed
that. I am anyway.
Hi, Claire.
Hi. Sorry, I just noticed the thing saying I need to share the whole screen on a Mac rather than just the slides. So let me just check after Kristen.
Yeah,
sorry,
for me it was fine.
No, sorry. Claire, that was me.
Yeah, that was Kristen. It's all right. Hang on, I will. Oh, sorry. Hang on. Sorry, I'm just sorting some things out on my screen. Before I do that, share screen. And then enter full screen. Do you see that?
It's not full screen yet. Now it's full screen. Perfect.
Yeah. Okay, great. Thank you.
Yeah. So Claire, it's good. Christine, we just saw, right?
Exactly.
Can I also test it?
And there is Benny and Song.
Hello? Can you hear me?
Hello. Hello, Kang.
Hi.
Try to share your slides to see that
Sure.
Fine.
Let me see. Here you should see my screen, and then I'll do full screen. Should be fine. Is it okay?
Perfect. Yeah.
Okay. Good.
Right.
I'll turn it off and then let other people to test, and then after that I'll just put my share screen on.
And then there is Benny.
To save time.
I think the last one during my session. Benny, are you there? He is not.
I can see him connected and unmuted apparently.
So
I think. I'm not sure. Maybe he's gone off for a cup of tea.
Yeah. It's BFL Word. Yeah.
Yes.
I see him, but hi, Benny.
Hi.
Oh, maybe I show myself. Hi, I'm Laura, your chair.
Okay.
Could you try maybe to share your slides so that we test it?
Okay, let's see. Let's see, can I find it? Where is it?
So there is this share screen arrow in green.
Yeah, I see that, but I'm trying to find the action.
Yes.
Oh, here it is. Yeah, okay.
Okay, so I see the screen.
And let's see, let me put it on full.
Yeah, would be great.
Let me see just
View, or if you do Control. You have to go to View.
Yeah.
And then there is full screen mode. Go down, scroll here. Here you go. Perfect.
Can you see it?
Very good. Yes.
Okay.
Okay, then if you stop sharing, then Kong can share his own slide.
Okay. All right.
Okay, so it's almost time to start. So first of all, I would like to introduce myself. I'm Laura Fabbietti. I work in Munich. I am an experimentalist. Working in the sector of strong interaction at the LHC. So I'm very happy to chair the second part of this first session. And we will have 4 talks, each of it, with different lengths. The first talk is 20 minutes long, including discussion. So Kong, please consider that you speak about 17 minutes. I will let you free to go and just maybe raise my hand or my voice in case you take too much time. Okay, so I think we are ready to go. It's a pleasure to introduce the first speaker. This is Kong Tu from the Brookhaven National Lab. And he will talk about azimuth and decoloration lepton jet and charge particle multiplicity measurements at ERA. So please, Kong.
Hi, thank you. Thank you for the organizers and invitations. As you can see, I'm very honored to, on behalf of both H1 and Zeus collaborations, talking about slightly 2 different topics. This is a combined talk. So about azimuthal decorrelations in lepton jet and also charge particle multiplicity distributions at H1. So a little bit of this introduction, a little bit of the big pictures. I think this is an audience that all familiar with that of the proton structures. I think, to my personal opinions, this is one of the most fundamental physics in particle physics, and is actually much more complicated than what was originally thought. Over the decades, different generations accelerators that we actually learned the proton structure is very complicated. And there are many of the big questions, for example, that is, I want to remind people that the mystery of confinement, I think we still haven't fully understood yet. And what is the pathway towards really figuring it out, the mystery of confinement, and also like examples of dynamic pictures for partons at high energies. So a little bit of the motivations, I think this started at the LHC. They have angular correlations in PP. So one of the observables that is commonly used, that you can measure a digest, and you look at the angular correlations. For example, you have a digest, you look at delta phi, and this actually probe to parton radiations, high order perturbative effects, and many other effects. And naively, you expect will be back-to-back jets, and then you expect the delta phi peak at pi. And then if you have some soft gluons radiates, and then you, of course, smear it out of your delta phi distributions. And this is indeed what the data has found. And then we also have next leading order calculations, and this describes, considering all this effects from, let's say, soft gluons, and this actually describes the data very, very well. And then taking these ideas, and then the recent developments in the TMD communities, they actually thought, okay, we can actually look at lepton proton collisions like in DIS, and then about looking at azimuthal correlation between the scattered lepton, for example, scattered electrons, and the jet. So this is actually found out to be sensitive to the transverse momentum dependent TMDs and published in PRL. And this is just looking at in the lepton proton center of mass frame. And then the idea was took by the Zeus collaborations, and they had this first experimental attempt to actually measure such thing by correlated lepton and jets. And this can access small Beer connects, Q-square dependence and non-perturbative effects. And then this is the preliminary results. I mean, the data is from HERA 2 with the highest center of mass energies, with a lot of luminosity, integrated luminosities back in HERA, about 330 inverse picobar. And then with the Q-square cuts, and also the jets of the ET is greater than 2.5. And the idea is you're looking at the delta phi distributions, and then you compare data to Monte Carlos. So here, the Monte Carlo is the Ariani, and then you can actually see the descriptions of data Monte Carlos are actually very, very well. But then if you go to maybe go to more jets, let's say jets greater than 3 or 4, and then you see at low angles, maybe the description is not so well. But overall, I think the Monte Carlos descriptions of the data is very well. And then taking one step further in EPDIS, so how does the Monte Carlo describe not only jets, but for example, the hadronic final states of particle productions? And then what's the role of gluons in particle production? I think these questions can also be explored in EPDIS. So one of the very recent ideas that actually published in PRL and also caught by the Science News media coverage, that in PP collisions from the LHC data, the physicists from Brookhaven actually found out there's hints of entanglement of partons inside of the protons. And the idea is really interesting because as from particle physics point of view, that we have very high energy collisions that we are boosting to this infinite momentum frame. And we are actually encountered a problem that the parts that you probe is actually collinear factorized with the rest of the proton. This is actually most of the particle physics actually developed based on. And then for example, PDFs and things like that. And then on the other side that we know the proton is colorless objects and there's color confinement and there's must be entanglement between the partons. So this actually comes into the new ideas of looking at the parton structure using the quantum entanglement. So the idea here is in DIS that we have high energy electrons having a virtual photons, and you define and you have probed a subsets of the protons defined as a region A. And you can see at the transverse directions, this is just 1 over Q. And then in the longitudinal directions, this is like 1 over X. And then you define the 2 distinct spatial domains, A and B. And then the predictions from the theorist is the entanglement entropy, the entropy that actually characterizes how much the system is quantum mechanically entangled, can be written down very simply related to the structure functions, for example, the gluon densities. So in the region A that you can see, this is basically determined by the inclusive scattering, and then you can determine the parton densities, and this gives you predictions of the gluon entropy. And then in the final state, you can use the final state hadron, and you can calculate the multiplicity distributions and see if this hadron entropy has any correlations with the parton entropy. So we use the H1 analysis also at the highest center of mass energies between 5 and 100 GeV square and Q square, and then the Y range. And we measure the charged particle multiplicity distribution PN in bins of Y and Q square. I want to make a remark there that H1 and Zeus did have many publications for charged particle multiplicities, but it's not exactly in the bins or in as the required from the model and data comparisons. So this is why we redo this very low Q square in the DIS in bins of Y and Q square in terms of multiplicity distributions. And we also, along with it, we can measure the moments of multiplicities. And we also measure this new observable proposed by this paper using the Hadron entropy. And then we do the Monte Carlo models compare with the data and also compare simply with the entanglement model. And here is just among many, many different plots and many data, I just want to show you one of the examples. So this is the hadronic center of mass frame, the eta star frame between 0 and 4, which is the current fragmentation regions. And then we have the double differential bindings in Y and Q square. As you can see, the Monte Carlo descriptions for high Q square at the right column actually describes the data very, very well. But then as you go into a lower Q square, the Monte Carlo starts to underpredict, at least for the high multiplicity tail. So I think this is a powerful data that can be used by even the Monte Carlo community to tune their Monte Carlo descriptions for particle productions. And then of course, the interesting part for us is the hadron entropy. I just want to remind you what the Hadron entropy is. So this is just the sum of the Pn, which is the probability distributions, times the logarithm of Pn. And then this Hadron entropy, first of all, compare with the Monte Carlos. For example, here we use RAPGAP. As you can see, that at high Q squared, this green data points and dotted line agrees very, very well at high Q squared, from high X to low X. But then as you can see, the Q square evolutions that when you go into low Q square, at the high X is still reasonably well, but then for the very low X, that in our phase space, this data Monte Carlo starts to disagree quite significantly. And then if you look at the data and theory comparison here, I want to explain the theory is using based on the Hera PDF. So we calculate the parton or gluon entropy using the logarithm of the xg. So is the gluon densities. And then this is the at different scale at 2, 5 to 40 GeV square. And as you can see, the data and the theory does not agree with each other. I think qualitatively the trend, you can see this is agree, but then of course the scale of the problem is much bigger than between the data and the theory. So I think there are many theory and development needs to be going into these directions, especially for the Q square evolutions of the entanglement entropy. But then this will be in the future work for the theoretical development. So this brings me to my summary. So this is the first studies of lepton jets correlations in EP, DIS by Zhu's collaborations. This is sensitive probe to the TMDs and also one of the first try of such measurements, and it's also going to be one of the measurements for jets at the electron ion collider based at Brookhaven. And then also we have the first time measurements of hadron entropy from hadronic final state using charged particles using the H1 detector. And this is a search for the quantum entanglement of photons in EPDIS. And this is a brand new ideas of looking at the photon structures in very different angles. And then the paper actually will come out very soon, hopefully by the end of the summer. So both measurements have set the baseline for future measurement experiments at the electron ion collider at Brookhaven for both EP and EA. As you can see, all of this physics probing the photon structures of protons can be embedded into a nucleus, and that we can probe the nucleus effect. So stay tuned for further developments from H1 and Zeus, and then there are many new projects that's actually ongoing. Thank you.
So thanks a lot, Kong, for this very interesting talk and also to be so full of results in such a short time. So I see Michel Sombera wants to comment first. So please, Michel.
Hello. I don't want to stop yes, can you hear me, please?
Yeah.
I don't want to spoil your joy of finding something new. I would like to point to the article which I have written in 1988 already with my colleagues. It's in physics letter B, and the title is called Entropy of Multiplicity Distributions, where we have actually analyzed that time multiplicity distributions of hadrons from proton-proton and proton-antiproton collisions, and we have found interesting, of course, that time DIS data were not available, yeah? But this is, maybe you should look at it, yeah?
Yeah, I think we did. I mean, it's, I think this time it was initiated by a new theoretical development, actually connecting. I mean, you can always measure entropy, right? I mean, there's always entropy there. You can always measure it. I think the ideas behind this was actually relate this into the structure functions.
That's true. That's true. Yeah, that
was new. I just want to point out that is new. Is not the entropy itself measurement has been done before. Yes.
Okay. Okay. Thank you.
Okay, no Marek Karliner wants also to say something. So please, Marek.
Yes. When you compare the measurements with theory predictions, can you say a little more? What predictions have you used? All theoretical predictions, do they agree with each other?
If you're talking about this one, so there's only one theoretical prediction now. And then this is based on a very simple entanglement model, okay? So I wouldn't say this is very developed, but the idea was looking at this DIS events, and then they use this 1+1D very classic conformal field theory to calculate the entanglement entropy. So this was developed not from high energy physics, but from condensed matters and other quantum informations. And then basically the idea is to relate the DIS kinematics where you have such a spatial domain defined by the 1/q, your virtuality of your photons, and also your 1/x, the kinematics variables. And then they relate this to the Hadron structure functions.
Whose work is this?
Dimitri Kazeev and I think Ian Levine.
Oh yeah,
this was.
I think I know this. Yeah. So.
Yeah, of course.
So
yeah, I think this was 2017, and they had these ideas, and then.
So it's a very specific model.
Yes, it's a very specific model. You're correct.
Thank you. Thank you.
I also have a question actually about the Hadron entropy and whether you also looked at this quantity to study the entanglement, looking at different Hadron species, separating, for example, baryon from mesons, and whether there is a sensitivity to the particle, to the PID.
Yeah, that's a good question. So from just very naive expectations from the theories is this work at the very low X limits. So when you're going to the only gluon dominance regions, this theory applies. And then in that sense, the naive expectation is it might not have a very huge difference between different flavors or species. So that's the naive expectation, of course. What it actually happens that we don't know.
Okay, probably future study will clarify that. Okay, so I don't see any other questions. So first of all, thank you very much, Kong, for this very nice talk.
Thank you.
And then I think we can move to the next speaker, who is Christine Lovasa. And she will talk about the precision measurement of single vector boson production at ATLAS. I see there is already the slides online. And Christine, you have 15 minutes in overall, inclusive discussion. I mean, just keep this in mind. Okay, so.
Yes.
Please.
So going straight to slide number 2, when we talk about the precision at the LHC, so with or without further discoveries, the LHC is currently the only machine to give more information about the Higgs boson or the standard model, the electroweak standard model. Some theorists have discussed 1% uncertainty. This sounds very extreme in the Hadron Collider environment, but if you look at the precision measurements of the Atlas W mass and the weak mixing angle measurements, they are only slightly worse than the Tevatron combinations, which are shown here at the bottom, the comparison. Now, the uncertainties here are dominated by the PDFs, which we can constrain basically using our own data. And we do have a wealth of data at the LHC. So if we look at the different center of mass energies, there's 2.76 TeV, 5 TeV, 7 TeV, 8 TeV, 13 TeV, with a wealth of data taken, the largest data set ever collected at a Hadron Collider. The luminosity uncertainties here are around 2%, but they are largely uncorrelated between the center of mass energies. And this gives us a unique opportunity to understand the proton dynamics over a broad range, a broad kinematic range. And ATLAS has published single boson measurements for all of the center of mass energies. This is illustrated here, where on the y-axis, you see the total production cross-section, and on the x-axis, the center of mass energy. And then you see the relevant publications, where here I'm restricting myself to cross-section measurements only for the rest of the talk, as we've already heard about the vector boson plus jets measurements before. The fiducial phase spaces for all of these measurements are very, very similar. So for the Z boson, it's lepton thresholds, PT thresholds of 20 GeV within a pseudo rapidity of 2.5 and a mass range of 66 to 116 GeV, with exceptions noted here in the colors that correspond to the measurements presented in the slide before. For the W boson, the kinematic requirements for the fiducial phase spaces measured are on the lepton PT threshold 25 GeV, neutrino PT threshold 25 GeV, and a pseudo rapidity of 2.5 with a transverse mass greater than 40 GeV. And again, small exceptions at 13 and 2.76 TeV are noted down. Now, if you look at the selections and you go to the detector level, then you basically see you have very, very clean signatures with very low backgrounds that are dominated by the lepton reconstruction uncertainties that are correlated over the channel. So you can correlate the Z and the W bosons and the W plus and the W minus boson separately. Before we go to the actual results of the measurements, if we look at the phase space at the LHC, the right-hand side illustrates the momentum transfer squared that is probed as a function of the Pareto momentum fraction for measurements taken at certain rapidities certain rapidities for different center of mass energies, 13 TeV, 8 TeV, and 2.76 TeV. For a resonance of approximately 100 GeV, you are around here. And then depending on, as the kinematics are determined by the center of mass energy, for a fixed mass and a fixed rapidity that you probe, for larger center of mass squared, you probe smaller values of X. And this has a distinct effect on the composition of gluon C and valence quarks that you probe. So if you go to look at the X dependence, valence quarks carry higher momentum, and the Q squared dependence for, if you go to higher resolution, you will see more gluons and C quark contributions. On slide 8 now, this is the WZ cross sections at 2.76 TeV. This is one of the most recent publications. Shown are the cross sections of the Z, the W plus, and the W minus. This is a small data set, which is still dominated by the statistical uncertainty, but what you find is reasonable agreement between the data and the predictions. For the Z cross sections, though all of the PDFs are slightly low, and then there are some larger disagreements between the data and the prediction for the W cross sections, where the best agreement is with the Hera PDF that only contains Hera data. All the predictions here are obtained using DY and NLO 1.5, which is calculated in next to leading order with full spin correlations. Next to leading order effects are included using Fuse for the Z boson and SUNS for the W bosons in the G mu electroweak scheme. This gives roughly 0.25% effect, and Fuse is used to calculate the PDF and scale uncertainties. The scales used are a dynamic MLL scale for the Z bosons and a fixed MW scale for the W bosons. And this also applies for the further results and further predictions that I will show, that I will compare to the results here. So on slide number 9, we have now the ratios. So the ratio of the W plus to the W minus and the ratios of the sum of the two to the Z boson. As you can see, the ratios significantly reduce the systematic uncertainties due to cancellations on the uncertainties and reveal a slight tension of the W plus over W minus data with the ABMP16 PDF set, which contains the 7 plus 8 TeV, LHC, WZ, and top data. The MMHT14 and CT14 and NLO sets are in good agreement in the ratios. They include the Tevatron as well as most of LHC data, and then except for the W plus C data for both of them. The WZ ratios are sensitive to the strange quark contents. And here it's the HERA PDF that is a little bit high and generally different from the other PDFs. It only contains the HERA PDF. And then if you include the Atlas WZ7TeV data, this yields the Atlas EPWZ12 and NLO set, which then is in very good agreement with the other PDF sets in the comparison. Now going to more differential measurements, this is cross sections at 5 TeV, center of mass. On the left-hand side, the rapidity of the Z boson, and on the left-hand side, the asymmetry, the W asymmetry measured as function of the pseudo rapidity of the lepton, and this is again compared with the DY and NLO predictions. There's a tendency of all PDFs to underestimate the central Z rapidity range, and the W asymmetry is also mostly slightly underestimated. If we now go to the 13 TeV data and look at the ratios again, WZ ratio, and on the left and on the right, here the W plus over the W minus, we see that the results here are fairly consistent with the run 2, with the run 1 results. So there's a preference for an enhanced strange content, though it's not visible for the 2.76 TeV data and for the W plus W minus ratio, which is sensitive to the UD valence content of the protons. There is a smaller ratio than is predicted by most of the PDFs. If we look back to the results as a brief reminder from the LHC run 1 data, this is the cross sections at 7 TeV, the most precise measurements of WZ cross sections at the LHC, I believe. This data is now mostly included in the newest global PDF sets. It has been interpreted by Atlas as enhanced fraction of strange C quarks. So this is the ratio of C to valence quarks roughly at 1, which you can see here on the right-hand side, though we don't see any strange, so there's no strange C suppression at low X. And Mark Sutton will talk later in the session a little bit more about the determination of pattern density functions of the proton with Atlas data. Then Atlas has also done some more measurements where more specific information through specific phase spaces can be obtained. So there's measurements on the high mass Drell-Yan data that adds additional information on photon-induced processes, where here you can see cross-section measurements as function of the dilepton mass up to 1.5 TeV. And on the right-hand side, we've also looked at forward Z production going to very, very low values of the rapidity. And this means going to very low values of X, which is also interesting for forward-backward asymmetry measurements. There's, of course, also the measurements of WZ production in association with jets that Camilla has talked about earlier. Coming to the conclusions, we have collected a wealth of single boson cross-section data at the LHC, and Atlas has conducted measurements at all center of mass energies with very low uncertainties with full correlation information, and we are looking forward to see this included in global interpretations. Thank you.
So thanks a lot. And I see there are already 2 questions. We start with Mandy, please.
Okay. Hi, Kirsten, and thanks for a very nice, comprehensive review of things. On slide 12, if I may. No, it must have been the one.
Yes.
The one before. Yeah. No, I only wanted to sort of clear up something that confused myself when reading it, so might confuse other people, because you say in the bracket ratio of C to valence C quarks 1. I think you just mean the ratio of the strange to the non-strange C quarks.
Yes.
This is nothing to do with the valence as such.
Yes.
Yeah.
Sorry. Yeah.
Okay, it's just a sort of typo. I just wanted to say that because people may be reading it and wondering what's going on.
Yeah.
Okay.
I'm sure I can still update the slides.
Okay.
Okay, so we have a second question. Shimon Surek, I hope
Almost perfect. You almost perfectly pronounced my name.
Okay, so please.
Hello, I'm Anthony.
Anthony, okay.
My question is about spin-spin correlations. I understood that not all approaches include spin correlations. I understood that only some of them include spin-spin correlations. So my question is, how important is spin-spin correlations?
You mean
when
for
you
the
ignore spin-spin correlation, is it big effect?
You mean for the measurement or for the predictions?
Not for the measure, for the calculation, because because you measure it correctly. But the question in principle, you should compare to theoretical calculation, which do include spin correlations, which maybe is difficult. I don't know. But my question is, how important is this? And which calculations include the spin correlations? All of them or some of them only?
So to my understanding, practically for all of the pure cross-section measurements of the WZ, this is compared to DY-NNLO, which has the full spin correlations. Now, this is probably not the case for the high mass Drell-Yan data, though I think there's probably a smaller effect. So their photon-induced production is a more difficult problem. I have to admit, I'm not entirely sure how important, for example, here on slide 8 for the 2.76 TeV data, or how large the effect will be for the on the calculation for the full spin correlation compared to no spin correlation. I'm not sure whether someone knows who is connected.
Thank you. Thank you.
Okay, so I don't see any other questions. So thanks a lot, Christian, for your very nice talk. And then we move to the next speaker, who is Benny Ward. We'll talk about the role of IR improvement in LHC FCC physics. So please, Benny, can you share your slides? Hello. So we have tried this before and was working. Hello, Benny. Can you hear me? Okay, maybe. He disconnected. He lost the connection.
I think he's still connected.
He's there but muted.
It's because I don't see him.
I mean,
he's there actually. I mean, I see him in the list. I don't know if there's something wrong with.
Can you send him maybe because what? BFL Word, yes. Ask you mute. So can you? Yep. No, this is right. So I wrote to him. Can you share your slide?
Where are they?
Hello. Oh, here you are. Very nice. Can you share your slide?
Yeah, I'm trying to find them again somehow. Just a minute. What happened? I don't understand what happened. Let's see, just a minute. It should be here.
Okay, should I share them? I can also do that.
No, wait a minute. I think I have it. Just
yeah, those are, yeah.
I have it. Just a minute. Let's see now. View.
Yes, exactly. Full screen.
Okay, now I need to go back. Let's see. That's a problem.
Okay, so while you are moving back.
Okay, now I'm ready. I'm ready.
Now you can start speaking about the role of the IR improvement at LHC and FCC physics. So
okay, I'm sorry about that.
Don't worry, no worries.
Okay, so thanks for the opportunity to be here to talk, and I'm going to talk about work with my student, former student, Bahram Shekharin and Scott Yost. And in the time I have, I'll make some introductory remarks and review the theory a bit and see how it interplays with the GLAP theory and the shower, et cetera, with some LHC data, in particular W plus Jets at 8 TeV, which we haven't shown before. And then finally, look at FCC discovery physics a bit and say some words about how it interacts with the precision work on electroweak effects at LHC in the context of these order alpha squared L corrections, and summarize. This is an ongoing story from the 1988 time when we were just arguing about how to do the resummation. Should we do the approximate one, such as we pioneered by Dave Jackson and Shari, or something more like the exact one from Yeni, Franchi, and Sura, in which, in principle, there's no limit to the precision. And Prince Barons was of the former approach, and we never really resolved it. And this discussion continues because these approximate methods are very practical and they gain large utility. And so today we have this in the form of a hard cutoff in the infrared and almost the very popular Monte Carlos versus the resummed approach that we've introduced with Hariri. And we also have it now in the context of ISR radiation from quarks, where QED PDFs with massless quarks versus exact Feynman diagrams with non-QED PDFs, and I'll come back to that. So it just goes on. And the error of 1% has been mentioned for these Hadron studies, and we believe our approach is the only way to really systematically achieve this type of precision tag, but that's a long story in itself. And so the theory we refer to as exact amplitude-based resummation theory, which we realized by Monte Carlo methods, and I have listed here some of the examples, so you can read those on the transparencies. And we've seen in the data that the improvement in the infrared that we advocate has made a difference in the comparisons with the data. Again, I have some references here where you can read that. And we have an ongoing effort to take these to the Fuse and other platforms, but we haven't done that yet. You should keep this in mind that we have a new law in the world, the SU2 left cross U1. QCD standard model theory is analog of the Newton's law for our generation. And it's 50 years celebrations have occurred, and it's good to keep this historical perspective that we were living at the time a new law of nature was established, and were able to actually participate to some degree in its establishment. The theory is here on the transparency, I showed the basic formula, the resummation part that's outside. There's also a part in here that's inside the phase space that you're familiar with. And these are the residuals that allow us to control things to as accurately as we can calculate the diagrams. But in principle, there's no limit to its precision, both for gluon radiation and photon radiation. And these are some of the formulas these are some of the formulas that we showed. This is the thing that we generalized from Yini, and these coefficients then involve both QED and QCD. And we can match it to showers, which is why we have Monte Carlos. And in the MCNNLO, which it's matched to, we have, in the process of being matched to, we have the usual split between the virtual and real corrections and counter terms, and the phase pseudocomp suppression penalty factor that sums up the big logs in a straightforward way. And again, we match into that with our residuals and with these formulas, so that's something that can work for, in principle, any of the Monte Carlos, and we are in the process of bringing that to fruition. The theory's error then is determined by how accurately we control the residuals. And the beauty of our improvement is that we don't have the plus function singularities that you get if you don't do our type of improvement. And to illustrate some of the results, I look on the applications to in MCNNLO, where we've improved the corresponding shower, and we're looking at W plus jets. And here we see with one greater equal to 1 jet, here greater equal to 2 jets. This is the first leading jet, this is the second leading jet. And you see the difference. Hariri represents our improved theory, Herwig represents the unimproved theory. And if you do the chi-squares in the soft regime, you'll see that the improvement improves the comparison between theory and experiment significantly. If we look into the third leading jet PT for 3 jets inclusive, or the the HT variable associated with the some of the Hadron jet PTs, then you see again that in the soft regime, that means in this regime over here and that variable, in this regime over here and that variable, we do get improved agreement between the theory and the experiment. And so it's encouraging that this improvement, which we started in the context of single Z production, actually holds also in the presence of gauge boson plus jet production. If we take these methods to the 100 TeV FCC collider, which I hope will continue, some of the recent comments have, I guess it has a 5-year period to show if it's feasible, which I guess we can cross our fingers on that. What we see is that the iron improvement actually does not destroy the discovery reach of the problem. In other words, if we have the key is that you choose the right scale. These points all have the dynamical scale that's referred to earlier, and these have what you would do if you have a fixed scale at, let's say, at the Z mass or some fixed number like that. And you see, you really do need to put in the dynamical scale to get the prediction, the estimates right. But our improvement, which is indicated with the, for example, this blue triangle, you see it's the upside down triangle. It tracks just through the points as well as the unimproved theory. So that's important. You don't give up anything, in other words, in very high values of the kinematics probe. And then finally, I want to turn, because I don't have so much time, but I want to turn to the precision, we have an unprecedented number of lepton pairs that have been made at the LHC. And you can therefore, as was indicated, probe the standard model. And it means you have to control the 1 alpha squared L corrections in the production of Z's and W's due to the tremendous precision of the data. And so we have invented the KK Monte Carlo HH Monte Carlo, which brings over precision we had at LEP 1 and LEP 2 to LHC. And the idea then is to look into those effects which heretofore have been taken to be small. So today I want to talk a little bit about angular variables and the forward backward asymmetry and the parameter A4, the coefficient of cosine theta and the angular distribution in the Collins-Soper frame for the, let's say, for this process. And so we have the standard kinematics that I show here. The phi angle is measured from the plane and it contains the 2 protons in the lepton pair rest frame. And we expect to get an interplay then between the different aspects of the calculation. And so we'll look into the type of observables that were measured at ATV by Atlas in this paper here, and where the electron weak was essentially treated as small. We get into discussion of how to do the calculation. The tradition is to essentially take massless quarks in the initial state, for the light ones anyway, and then put in PDFs with corresponding QED PDFs, if you want to call them that. The best ones around now are the so-called Lux QED ones. Or our approach, in which we actually calculate these things from first principles using the quarks and the quarks masses, which are fundamental parameters of QCD. QCD is not a massless theory. The quark masses are in the PDG. And the question is, how do these two approaches relate? Here we have the transverse degrees of freedom of the radiation of photons in the initial state. There they do not, for example. And therefore we expect that as long as we're not looking at transverse effects, we won't see so much difference. But if we do look at transverse effects, we expect to see some. And I just want to illustrate a little bit in the time I have left, because I'm only supposed to take 12 minutes in the talk. So this gives you the kinematics. It's an Atlas type kinematics, cuts on the leptons, et cetera, similar to what you heard earlier. And you can look at where you want to do FSR with our approach in a non-QED PDF, FSR plus ISR, non-QED PDF. All of the stuff, non-QED PDF, and you can put in the Lux QED, FSR, for the initial state, so the collinear approach, and there use our Monte Carlo to realize the corresponding NLO plus QED. And we can therefore compare these, and I think it's quite remarkable to see that you have to remember that the precisions are at the fraction per mil level, and we see those effects because of the large statistics that they do have. So here I take the uncut, and you can look to see the differences between when you have no ISR, when you put in the collinear, the traditional 30-year approach that we're trying to change, and or whether you use our ISR and you see you get differences in the per mil level differences. And if you go to the asymmetries, you can see these coefficients even have initial final interference effects that need to be taken into account in some cases. For example, and here I've already gone to this transparency. This is the angle distribution in the Collins-Soper frame, And you can see the fractional contributions. When we don't make cuts, it's to project out A4 because of the orthogonality of the various polynomials. And when we do make cuts, we use AFB in that case. But you can see that we have this ISR, which had essentially been ignored, enters at the permeable level, which is the level of their measurement. I'm sorry, and so I went the wrong way. And so finally, these methods allow us to combine the KK Monte Carlo with the R improved shower, and you see there is an observable effect in the Z transverse momentum that has been, again, the one that we've already demonstrated is there in previous work. So let me sum up. I'm a little bit out of overtime, but not too much, I don't think. Precision theory involves control of both the infrared limit and the variable minimum fraction going to 1, and the collinear limit where PT is going to 0. You have to really control both of them. If you just integrate out the PT, which has been the traditional 30-year approach, you integrate over PT and look at just your incoming partons as linear objects. There's just some physics at the LAC that you just won't be able to discuss. That's what we've shown in this short talk. We now have control over both of them for those that wish to do so, and we're in the process of making contact with the NLO QCD in this Monte Carlo with my student in Siad Makinyadak. And I just want to say that given we haven't seen new degrees of freedom, that not taking these effects into account may obscure possible things beyond the standard model at both LAC and at the FCC. It just may do it. Thank you very much.
So thank you very much for this interesting talk. Are there questions or comments? I see Marek wants to ask something. Please, Marek.
Yes. Hi, Benny.
Hi.
On page 17,
yeah.
If you look at the
page 17, let me get to page 17. Let's see. Is this one?
Yeah. So the predictions which use infrared improvement agree with some other predictions in all points except the highest one at 12. Why is that?
Well, it's a question of you mean you're talking about this area here?
Yes, yes.
Okay, so in this fixed scale business, I think the problem that happened here was statistics. So while this looks big, we just didn't have many events out here, Marek. So it's within, if I put the statistical errors on all of them, which I haven't done.
So you say I shouldn't take it seriously. This is a statistical error.
Yeah, because that's at the end of the plot and we didn't have enough events. Right?
Thank you.
Okay, so since we are running late, being already late, I would then thank the speaker again. Thank you very much. And move to the next talk. That will be given by Claire Gwynlyn.
Yeah, hi, Gwynlyn. Yeah, just waiting to be able to share my screen.
Yeah. And
did Raj have a talk? I have a question.
Pardon?
It looks like Roger may have had a talk. I had a question, but maybe I don't see it right.
No, there is nobody having a question.
There's nobody? Okay, very good. Okay.
No, sorry, I checked, but there is nobody raising their hand.
Okay, that's fine. Thank you. Thank you.
You're welcome. So you have to stop sharing so that Claire can start sharing. Okay, perfect. Yeah, Claire, you can.
Yeah, I'll just take us to full screen.
Yeah.
Let me know.
So the next speaker is Claire Gwynlan from Oxford, and she will talk about precision QCD at the LHEC and FCCEH. Please, Claire.
Thank you. Yes. So, yep, that's what I'm going to talk about. Yeah, precision QCD studies at these proposed future lepton-proton colliders, the LHEC and FCCEH. So I am going to primarily focus on the results of the very new LHEC white paper that is in the process of being submitted today. Okay, so just to kind of motivate and set the scene of a lot of what I'm going to talk about, it's just kind of useful to just remind ourselves of the situation today in terms of our knowledge of proton structure. So I'm showing here the gluon PDF uncertainties on the left, and also you can translate PDF uncertainties into these luminosities, where you can just read off the size of the uncertainties as a function of the invariant mass that you're interested in. So it's very obvious to notice that the uncertainties are very large in the high X region and also in the small X region, essentially where we either have no data or where the data exists it suffers from quite large uncertainties. And so, for instance, this high X region translates directly into high mass and so impacts on new physics searches at the LHC, for example. And even in the medium X region where we know PDF's best, that's precisely where things like Higgs production sits. And so for these precision measurements of Higgs and top and vector boson production, we still need to know things a lot better. So in fact, it is the case that already at the LHC, PDF uncertainties are becoming limiting for us. So for example, I've just stuck a few examples here. You can sort of peruse as I'm talking. But for example, in BSM searches, we're limited by the very large uncertainties on the high X gluon and quark PDFs, and it can kind of hide our ability to discover new physics. And also precision standard model parameters, such as the mass of the W or sine squared theta W, are also limited by PDF uncertainties, which tend to be the dominant uncertainty. And crucially, Higgs as well, you can see here, the dominant theory uncertainty at the moment is a combination of the PDF and alpha S. So really, this is becoming limiting if it's not already at the LHC. And it is already for many processes. And so in order to really maximize and optimize the potential of these Hadron machines, we really need a transformation in precision in terms of our knowledge of proton structure and also, as we'll see, alpha S. So how to do that? That brings in the EP colliders, which are, essentially massive electron microscopes. So they are the cleanest, highest resolution microscopes that we have at our disposal that we could build today. So these are really ideal QCD laboratories and the best, by far and away, the best way to probe proton structure. So I've just put the Feynman diagrams here for the inclusive neutral and charge current processes. So the LHEC and FCCEH, they're proposed future lepton-proton colliders. The electron accelerator would be an energy recovery LINAC. So this has been identified in the recent European strategy update as a high priority future initiative for CERN, the R&D into that. The LHEC would be attached to the high luminosity LHC, so shown here, or later on you could have an FCCEH attached to the future circular collider. The electron beam energy would be up to 50 or 60 GeV, and so colliding either with the 7 TeV protons of the LHC or the up to 50 TeV protons of the FCC. These are high luminosity machines as well, so we expect about 1,000 times the integrated luminosity of Hera per 10 years of operation. And I direct you to a couple of other talks in this conference as well to find out more about the machine and the detector plans. So I mentioned the LHEC white paper, as I say, being prepared for submission today. This is an update to the LHEC CDR that was published in 2012, and it's a really comprehensive compilation of new and updated studies, culmination of the work by very many contributing authors. So I'm going to talk or summarize some of the results on precision QCD and proton structure, but I direct you also to some other talks in this conference which really highlight the very broad physics program of these machines. So here's an illustration of the kinematic coverage in terms of Bjorken X and Q squared. To date, HERA is still the world's first and only lepton-proton collider. So that's its coverage is illustrated by this yellow blob. And the LHEC extends in both 1/x and Q squared by a factor of about 15, that's shown in blue, and the FCC a further order of magnitude again. So this is really an unprecedented increase in kinematic reach. These are high luminosity machines as well, so able to obtain precision PDFs up to close to X of 1, and of course explore the very small X region, this novel region here as well. And it does it in an environment that's very clean experimentally and also theoretically. So you're free from higher twist, you've got no nuclear corrections, it's a proton collider, and also very sophisticated theory will be possible at that time. So the studies I'm going to present are based on simulated data. You can get the full details from the white paper. Something just important to mention is that, of course, to sort of for this to be optimal and of maximum use for the LHC, you want some period of concurrent operation. So I direct you to this paper with a projected timeline, but just to say that you know that the plan would be for some years of concurrent operation with the high Lumi LHC, plus a later dedicated run to sort of complete the data set to enable the LHEC to fulfill its full physics potential as well. So I'm going to be showing results for mainly two different scenarios. One which I'm calling the LHEC first run. So that's just the first 3 years of operation, just the first 50 inverse femtobarns of data. And then another scenario which I'm calling the LHEC full inclusive, so the inclusive neutral and charge current, but the full data set. So about an inverse attobarn of electron data, supplemented with some positron data as well. Also a couple of other data sets which are in there, but actually they don't have too much impact on the PDF results that I'm showing, but it's there for completeness. So the QCD analysis follows the HERA PDF 2.0 ansatz, but is slightly more flexible. So more details on the exact parameterization are in the backups. And just to mention also that for the fits where only the inclusive neutral and charge current data are included, those data sets are sensitive to the sums of quarks and antiquarks. So that leads to a natural parameterization, which I'm calling the 4+1, of the valence quarks, and then the total up-type, the total d-type, and the gluon. However, these machines also allow for very precise semi-inclusive measurements of heavy quarks, for example, so strange and charm and beauty. When you do that, you enable a complete unfolding, including quark flavor as well. So I will show 1 or 2 results with that, and in that case, got a more flexible parameterization where you split up the quark flavors as well, because you can then pin down everything very precisely. So the first set of results, I'm showing the valence quark PDFs here, just shown as a ratio, the UV on the left, DV on the right. And the first thing you notice is the very high precision from the LHEC predictions, they're shown in yellow and blue. And one of the things to take away is that most of the benefit is gained in that first 3 years. So the first LHEC run shown in the yellow. You do see that for the D-valence, there is some benefit here from the full data set, but actually that is dominantly coming from the inclusion of positron data, because that gives you some extra sensitivity to the D quarks via the charge current. So this is a hugely precise determination, and in the high X region, this is going to be crucial for beyond the standard model searches. It's also relevant for Drell-Yan and the measurement of the mass of the W, and also we'll be able to resolve the long-standing mystery of what actually is the value of the D over U ratio at large X. So at the moment, there's conflicting theory pictures. The data is inconclusive. So this gives a very clean and precise measurement right up to high X. Here's the gluon PDF on a log X scale on the left and a linear X scale on the right. So current data in global fits extends down to about 5 × 10⁻⁵ in X. So the LHEC pushes down more than more than an order of magnitude lower, the FCCEH another order of magnitude. So that gives this really unique opportunity to explore small x QCD, which I'll talk a little bit more about in a few slides' time. And then here in the high X end, the gluon's very small, but very poorly known at the moment. And very important. So this precision determination at the LHEC will really have a crucial impact for BSM searches. So those results that I've just shown are based just on the inclusive data only, but as I mentioned, the LHEC is able to allow very precise measurements of semi-inclusive processes, so pinning down the strange, the charm, and the beauty quarks as well. And in particular, we've heard already today a little bit about some of the open questions to do with the strange PDF, which is poorly known, and there are questions to do with, is it suppressed with respect to other light quarks? Is S equal to S bar? Well, at the LHEC, it will have direct sensitivity via charm tagging and the charge current process, allowing this precision XQ² mapping of the strange density for the first time, as illustrated here. And in addition, very high precision measurements of F2 charm, F2 beauty will be possible, so enormously extended range and much higher precision than was possible at HERA. Also, studies indicate that the mass of the charm and beauty can be determined to sort of the level of a few MeV, which also has wide-ranging consequences on the LHC program. So inclusion of these kinds of data sets, as well as the inclusive, really allow a complete precision unfolding of all quark flavors. So here's a summary of these PDFs. So this is kind of illustrating the situation today. It's the PDF for LHC 15 PDF, and then what we might expect after the LHEC first run, with, of course, further improvements if you were to use the whole data set or to include some of these heavy quark measurements or DIS jets and so on. Useful always to look at the PDF luminosities as well, because then you can read off the uncertainties as a function of your mass of interest. And you can see this really strong constraints, extremely high precision across the whole mass range. So the yellow here is the LHEC first run again. The blue here, I should point out, includes the full inclusive data set, but also has the addition of some of this heavy quark, strange, charm, and beauty data that I mentioned as well. And you can see this really high precision projections right up to high mass. So this has direct consequences on the LHC physics program, of course, and notably, not only are these PDFs extremely precise and obtained in a very clean way, experimentally and theoretically, but also external. And that's kind of important because although the LHC itself can give some constraints, what we've got here is something that's very reliable, external, not, for example, muddied by potential contamination from new physics itself. And so that's what's really needed, both for range extension and for interpretation as well. So I'm just giving a few examples of the impact that this improvement has on the LHC. You can find more examples in the white paper. These two plots are slightly old, but illustrate the point. They are two examples of BSM searches, one sensitive to gluon PDF and one sensitive to quarks. It's the cross-section uncertainties, basically. So these bands are showing you the very large uncertainties coming from modern PDFs compared to what one might expect in the red from after an LHEC. And this kind of translates into an improvement in mass reach of, half a TeV up to a TeV, depending on the exact process you're looking at. Another example is the Higgs, which, as I've mentioned earlier, is dominated, the theoretical uncertainties are dominated by PDFs and alpha S. So all these colored blocks are showing you the PDF uncertainties from various different fits. And also, if you look, for example, at the three blue blocks, then that is actually the same PDF, but the predictions assuming a different value of alpha S. So you see the spread that you can get as well. Compared to on the right, the LHEC projection, and this box includes both the PDFs and alpha S. as it is expected after an LHEC. So I'll talk a little bit more at the end about the prospects for alpha S determination as well. So the take-home message basically is that an LHEC or an EP high energy collider can transform us into a situation where the PDF and alpha S are subdominant now. And the same conclusion is true for things like MW and sine squared theta W, and you can see more about that in the white paper. Okay, so I want to talk a little bit more about small x QCD now, because that's what these machines are really uniquely, it's really unique in their ability to explore that kind of novel kinematic regime. So we expect to see new effects. We expect the breakdown of DGLAP at small x and the onset of BFKL dynamics. Maybe we see something gluon saturation phenomena. But it's really quite recently that we think we've seen, we sort of believe that we have seen evidence of the onset of BFKL dynamics in HERA data. And that's illustrated in this plot where you see a HERA reduced cross-section compared to, in purple, a calculation with small x resummation included, which fits the data much better, particularly in this small x region, than a pure DGLAP prediction shown in green. So the LHEC and FCC have this 1 to 2 order of magnitude extension down even to smaller x, so have massively more sensitivity to explore and discriminate what's going on at small x. So not only would this be milestones, huge milestones in their own right to sort of discover something new and to be able to explore that region, but also it does have impact on Hadron Collider phenomenology as well. So here's an example of the gluon fusion cross-section, so without and with the effects of small x resummation as a function of center of mass energy. And you can see that as you go up, particularly up as far as the FCC, then these effects are really quite sizable. So it is going to matter whether we understand what is the correct treatment at small x. So just to illustrate the sensitivity of these machines, I'm showing here predictions for the F2 and the FL structure function, so with and without small x resummation. And these points here are the LHEC and FCCEH pseudo data, extremely precise, and so able to discriminate between these two different treatments. And for FL, you see the differences are even larger. So, that's highlighting that a direct, precise measurement of FL also has a critical role to play here. So you can go a little bit further. So a study's been done where some pseudo data has been simulated, including small x, so LHEC and FCCEH. And then it's been fitted with a pure DGLAP and a consistent theory that also includes small x resummation. And these are the results, the chi-squared per degree of freedom. And what you see is that we get rather large chi-squareds for the pure DGLAP, coming much lower when you use the consistent theory, indicating that one can start to recognize something's going on here. And the FCC, of course, has a larger, more obvious effect because it probes down to even smaller in X. So yeah, the results of the fit you can see here. This is the gluon uncertainty. And if you just focus on the orange compared to the green, these are fits which include all of the LHEC and FCCEH pseudodata, as well as HERA, in fact. But the orange has small x resummation included, the green doesn't. So you can see the quite substantial difference in the extracted gluon. And I've just highlighted this, approximately 15% around x of about 10 to the minus 5. That is a much larger difference than the precision with which you actually expect to be able to extract the gluon, which is more of the order of about 1%. So these things together really highlight the large discriminatory power of these machines, the LHEC and FCCEH, to pin down the details of what's actually going on at small x. So you can go a little bit further as well, because not only do we expect small x resummation effects, but also we might expect to observe gluon saturation. So that's going to manifest as some deviation from linear DGLAP. So the study that's been done is to produce two different classes of pseudodata, one based on DGLAP only, and one including the effects of saturation as well at small x. And then you can fit both of those classes of data with DGLAP only, basically to see, can my fit recognize that there's something wrong here, that there's something inconsistent. So what you're seeing on the left is the DGLAP-based data versus the DGLAP theory. So it's a chi-squared over number of data points. The blue indicates just the comparison before anything is fitted. And then the red is after the fit. So here you see what you might expect. It's consistent pseudo data in theory. So it's a pretty good chi-squared distribution anyway, and then it gets a bit better after it's fitted. And then over here, you see the same thing, but for the saturation-based data. So you see a very poor chi-squared initially, and then it does get quite a bit better after the fit. That's kind of indicating that the DGLAP theory is able to sort of absorb or fit away some of the differences between the theories. But then if you look at the post-fit distributions from each, that's shown down here, you can see that there is still a difference, right? It cannot fit away everything entirely. You can still recognize that this has a higher chi-squared than the consistent case. But you can go a bit further anyway. And investigate the origin of the worse agreement. So what I'm showing here are the pull distributions in 4 different bins of Q-squared, or for 4 values of Q-squared. So the pull is the data minus the post-fit theory prediction over the experimental uncertainty. And if you focus on the red, which is the saturation-based data fitted with DGLAP, you see that at the very smallest values of X, the theory wants to overshoot the data. At slightly higher X values, it wants to go the other way. But therefore, what's happening in the DGLAP fit is that it's trying to, it's sort of trying to accommodate this tension, and that results in the higher chi-squared, and it's a sort of slightly skewed fit. But the important thing to be able to kind of recognize linear versus non-linear QCD dynamics is to have a large Q-squared lever arm, because even though maybe you could accommodate a different X dependence, you could absorb that into the PDFs at a particular Q-squared, you couldn't also absorb a Q-squared dependence. And that's how these theories differ, right, in their different Q-squared scaling. So this large lever arm in Q-squared is crucial. It's exactly what these machines do, right? A massive kinematic reach in both X and Q-squared. And just to flip back one slide briefly, what that means as well is that one could get more significant results or more significant separation here if you were to focus in on the Q-squared bins where you expect saturation to be most prominent. Just a quick word on FL, because I mentioned that it's also got a critical role to play. So this is in red, this is a simulation of what you might expect from the LHEC if you could do dedicated runs with lower electron beam energies compared to what we actually managed at HERA in the green. These data are not included in the studies that I've just shown. So you can expect an even more substantial, discriminating power if we were able to make such a measurement, because it's actually quite difficult for an incorrect small X treatment to accommodate such a precision measurement as this, and F2 as well. So I just wanted to mention that briefly. Okay, so in my final few minutes, I just want to talk about the prospects for determination of the strong coupling at the LHEC. So this is the least known coupling, but obviously crucial for Hadron Collider programs. It's needed for cross-section predictions, including Higgs, as I've highlighted already, and to constrain gut scenarios and many other things. But the issue we have is that the current measurements are not all consistent. There are open questions as to what is the true central value, what's the uncertainty. Alpha S and DIS always seems to be lower than the world average, but lower than measurements from other processes such as jets and E+, E- or tau decays, for example. And so we don't really know. There's a lot of open questions here. So in the next few slides, I just want to talk about the prospects for very highly precise determinations from the LHEC. And we can do that using both inclusive data and jet data. So on this slide, I'm talking about the inclusive data extraction. And we use, much as Mandy talked about earlier, you can determine it in a simultaneous fit to both the PDFs and Alpha S. So that's what's been done here. And it's been done for 3 LHEC scenarios. This first run in blue, then adding in some positron data in green, and then the full inclusive in red. And you're seeing the Alpha S uncertainty as a function of the assumed uncorrelated uncertainty, which turns out to be the dominant one. And so I've kind of highlighted a particular value here. So the full inclusive data set with an assumed 0.25% uncorrelated uncertainty, that can get you to per mil precision from inclusive data alone. And you can see that even from more conservative systematic scenarios or from smaller data sets, you can still get dramatic improvement over the current world average, which is indicated by this dashed line here. We've also got jet data, which is very sensitive to alpha S. I see I'm getting close to time, so I'm going to skim over this particular slide just to say that the DIS jet data in neutral current is, well, indicated here. It's very sensitive to alpha S as well as the gluon, in fact. And so we've simulated some pseudo data here using next to leading order predictions and done a full consideration of systematic uncertainties as well. And then alpha S has been determined in a NNLO QCD fit to those data. Alpha SMZ is treated as a free parameter. So this is the result that's obtained, again down of the order of per mil experimental precision. It's the scale uncertainty that dominates actually. So it's probably going to be the theory that's the limiting factor. You can play about with that a little bit and get a smaller scale uncertainty if you restrict to sort of higher PT data sets, for example, but then you're trading off and you correspondingly increase your experimental uncertainty. But maybe we'll have by the 2030s, NQ Delo for jets. There's probably some people here connected that can talk about the prospects for that with more authority than me. And something else you can do as well at the LHEC is test alpha S running over a very wide range in scales. So you can do the same kind of fit, but restrict to subsets of data. The results are shown here in the black points, and you see these very high precision points. Below scales of 200, each individual one of these points is more precise, more experimentally precise than the current world average. And uniquely, the LHEC, this determination is connecting low scales through to the Z pole and even higher, in a single experiment. So real stringent test of the running of alpha S. So this is the summary of the alpha S projections from the LHEC shown here in blue compared to other current NNLO determinations. These top two are the ones I've talked about, so the inclusive DIS only and then the jets only. We can also, if we find that these things are consistent, you can put them both into a fit as well and do even slightly better. And even with the first run, and even with only inclusive data, you can still get a value that's better than the current world average. So the ultimate precision here is on a par with the, it's of the same level of the alpha S projections from FCCEE. So we're talking about, two independent, hugely precise, per mil level determinations here, which hopefully can also resolve this question of whether alpha S in DIS is actually smaller than that in E plus E minus, for example. Okay, so I've come to the end. So just to summarize, Energy Frontier EP colliders are really essential if you want a full exploitation of Hadron, both colliders, both current and future. It's giving you this external high precision PDF input, complete QGM folding, exploration of small x, strong coupling to per mil precision. The results I've talked about are summarized in the white paper along with many others, which other talks in this conference will talk about. And I've just put these 3 points as, I guess, the take-home messages from my own talk, which is that all the critical PDF information could be obtained early on in the first run. You can get alpha S to per mil experimental precision. That's also achievable early with the use of DIS jets as well. And you've got this unprecedented access to, a new kinematic regime to explore small x phenomena. Thank you, that's it.
Okay, so thank you very much for this very interesting talk and exhausting list of goals, physics goals for the future facilities and current searches. I see that Marek has a question. Please, Marek.
Yes. Claire, can you say a word about polarization?
I can. It depends which polarization you mean. So the electron beam would be highly polarized. So in fact, I didn't make a deal of it because it doesn't have a big impact for the QCD studies. But the electron beam would be.
Oh yes, it does very much. Well, if you polarize both the nucleon and the
nucleon is not polarized. That's what I mean. So I'm saying only the electron beam would be polarized. And that is very important for electroweak studies. Also, the high negative polarization gives you a much larger cross-section for Higgs studies, which will be talked about extensively in a different talk. But this isn't a polarized nucleon machine. This is a polarized electron beam. Yeah.
Okay, thank you.
Okay.
I also have a question about BSM. To your opinion, which is the best channel to look for BSM at the future facilities, for example, at the Electron Proton Collider?
Well, there is a whole talk that is focusing on the BSM studies, the unique, because it does have some unique sensitivity. So certain leptoquark channels, for example, this machine has sensitivity that no others do. So there is two aspects to this machine. It has a whole program in its own right of BSM, of Higgs, of electroweak, but then it also has this other side to it where it by virtue of these precision QCD measurements, it transforms the LHC into a much more highly precise search machine as well. So I think that's a difficult question, which is the best channel to look in, because I really don't know what might be out there. We need to look at everything.
Okay, thank you. So are there other questions or comments? So if this is not the case, thanks a lot, Claire, for this very nice talk. Okay. So we come to the end of this, let's say, second part of the afternoon session. Now we will have, I guess, 10 minutes break, right? And then we resume again, right?
Yeah, I would like to say that if the speakers of the last session are connected, it would be a great time now to check the slides. So I think most of them are connected right now.
Hi, Racha.
Hi, Daniel. How are you?
How are you doing?
Nice to meet you. I like the background.
I changed it now. Okay.
Thank you.
Let me try to share my screen. I was just remembering that this is not the first time we are in a conference with a catastrophe.
Yes.
Right? Remember DIS.
Good. We see the slides.
Yes,
you want to try having them? Yeah, perfect. We see them.
Okay.
Very good.
Great. So I stop sharing.
Thank you. And the next one is going to be Kresimir. Are you there?
Oh, I'm here. Sorry. Do you hear me? Yes. Okay. Sound is okay. Let me share my screen. So, right. Does it work?
You can see the slides. Yeah. You want to try the full screen mode?
Oh. So you see just a part of them.
Yeah, we still see the two parts. So if you want to put them in the full screen mode, we will see the
I'm not sure I can. Let me just think a bit.
Take your time.
Full screen mode.
You have a view up top. Would that work if you go there and start?
Yeah, I'm just, but that will not help, I think. Now I'm technically in a full screen, but I do see it as a full screen now. Oh.
Presentation.
Now just let me give a sec.
Here is a presentation, second from the top.
Yeah. So just a second, stop share. Let me try again. Now if I do it like this. Yeah, I tried yesterday and I recorded it. It looked nice. So this is not a full screen, huh?
Yeah, it looks small.
Okay, let me try something else. Okay. Right, exit full screen. No, I think if I do it, I should just share this particular Acrobat reader and then, so what you're seeing now?
We still see it in some kind of PDF format rather than a full screen format.
Yeah, but this is actually a...
Can you go to Indico and try to share it on your behalf and see if it works any better?
Well, so,
I mean, this is fine. In principle, this is fine. We can see everything.
So it's smaller than full screen. That's what you're saying, right?
I mean, this works in principle. If this is all you can get, that's fine.
Okay, you can check out the speakers and then I can maybe make some more experiments and then we can try again.
Thank you.
Maybe, huh? Okay.
Is Ritu here? Ritu Agarwal?
Yes, I'm here.
Sorry, hi. Did I pronounce your name correctly, Ritu?
Yes, you did, yes.
Very good. Can we check the slides?
Yes, but are we going ahead of time?
No. We are in the break session right now. We have 10 minutes of break. We want to just check the slides ahead of time to make sure everything is.
Sure. Yes, I will just share my screen.
Yes, we see the slides.
Okay.
Okay, very good. The next one will be Agnieszka. Are you there? Thank you, Rito.
Yes.
Agnieszka Kudzak, are you there? Okay. Is Sarah Taheri there?
Yes, I'm here.
Perfect. Can we check the slides?
Yeah, sure. Can you see?
Yes, we see them. Very good. Thank you.
Thank you.
Is Mark sat on there?
Yeah, I'm here. So
Okay.
I'm not entirely sure what to do, so bear with me a moment. I will just share. So I presume I have to share the entire screen.
Yes.
Oh, actually, I don't know. Actually, so what about, is that sharing? And,
yes, but not in the full screen mode.
Yeah, hold on a second. I just need to. What about now?
Enter full screen. Yeah,
is that
we
full
see.
screen? That's full screen, is it?
Yeah, and it's visible.
And then changing.
Did you change the slide?
Yeah.
Yes. Now we see it. Thank you.
Brilliant. Excellent. Thanks.
Perfect. And then Michael Tambera.
Okay, I'll try.
Okay.
I can't stop.
But I am okay now. And can you see it?
Not yet.
Yes, you can see it. Yeah, and I
yes, we see it.
And that's it. It's moving. Yeah, fine.
Not yet. Did you change the slide?
I changed the slide now.
We are still with the first one.
Oh, I'm sorry. Oh, it's in my Acrobat. But somehow, I don't know. Okay. I did something wrong.
Okay.
Control L. Does Control L do it?
Control L.
Yeah. No. Okay.
And now you can see it.
We see the first slide still.
And we can still see the toolbar across the top as well.
Oh, but my problem is that I don't see the. Okay, so I go escape. I stop sharing. Now there is resume share. Yeah. Wait a minute. I don't. There is something strange which never happened to me. Taking. Talk. No. Take. I don't know what is. New share. Okay, I try new share. Okay.
Okay.
I try this. Okay. Can you see it?
We still see just, okay, now they moved, but no, now it vanished completely from the screen.
Okay, so can you stop me somehow and I will try for the second time. I don't know how to get from.
Try changing page now. Yeah, that's done again.
Okay.
Yeah, that's changing.
Yeah, but not in the full screen mode. That's what's my.
Yeah, we can still see a toolbar.
Yes, so let me go to Control L. Okay.
Right now change the slides now.
Can you?
Yeah, that works.
Yeah.
Okay, great. Thank you. So I hope during my presentation, it will not break down. Thank you.
Okay, thanks a lot.
Hello, can you hear me? My name is Agnieszka.
Okay, shall we test the slides?
Yes, I would like to try. Can you see my slides?
We do see them, but not in the full screen mode yet.
Okay.
Now we see your browser.
Okay, so Control N. How to do full screen?
It depends on what you are using for your slides. Like for me, I just go to the view mode and say full screen mode, and that's it. I'm not sure what you are using.
That looks like Chrome web browser, doesn't it? Is that a web browser you're looking at?
It's Internet Explorer.
Internet Explorer. Can you download your slides so you're not looking at them in the web browser? So is that icon at the side on the top left there? Is that a download icon? Oh, there's full screen. That would be full screen, yeah. But that's full screen in the browser still, isn't it? Okay.
And now?
That's still in the browser. I think you might need to download it and then view it from view the downloaded version, not in the browser. That's rotating.
I couldn't find.
Try that one. Press the one next to that one. No, right. That might be. Okay. And what if you press it down now? Does it just scroll or does it change page?
I couldn't now stop that.
Nishka, maybe you should share your local copy on which you have on your computer.
Sorry.
So do you have a copy on your computer yourself?
Yes, but now sorry, I share the screen.
Did you share the screen? Because we don't see anything.
I don't know.
We see the screen now. That's still the web browser again.
But it's on my desktop.
Could you right-click it? If you right-click it and see if you can open it in something else instead of the browser, you might be able to open it in a program which you can view. So if you right click on the PDF, you might be able to.
I click on PDF.
Right click on it with the right mouse button. It might give you an option that you can open it with something else.
I don't know. I have a PDF, but maybe someone could share. I don't know.
I can share for you if you want.
Yeah, let me go to the Indico and see.
Yeah.
Where are we? Okay, let me download it. Okay, and now let me see if I can share. So now I don't see the Zoom window. I have it on my desktop and I don't see the Zoom window myself now with the share. All right, so can the host try to share on her behalf?
Yeah, I can share them.
So she's the fourth talk in the schedule.
Yeah, she just need to tell me when to switch the slides.
Agnieszka, are you there? We do have to start actually in a bit, so.
Yes, I'm here.
So the host will try to kind of share on your behalf. Is that okay?
Yes.
Okay, so can you go ahead and please try to see if you can share them? That's the fourth talk on the schedule. What is going on? Okay, is the host there? Hello?
Yes, I am around. So
I think
we can go to the first talk, and I will share the slides for Agnieszka then.
Thank you. Thank you. I'm sorry for
no problem. Okay, so welcome back to the Strong Interactions and Hadron Physics session. I will be chairing this last part of our schedule, and we are happy to have as our first speaker Daniel de Floyan, who will talk about soft glue and effective coupling. Please go ahead, Daniel.
Thanks, Racha. Okay, so I will talk about soft glue and effective coupling, and this is work done in collaboration with Stefano Catani, Massimiliano Grassini, and also work in preparation with Simone Devoto and Javier Masitelli. So the outline of my talk is very simple. I will give some introduction and I will show some results at next to leading, next to leading order and beyond. And I will finally show a pretty interesting relation that we call the conformal relation, which is valid to all orders for these couplings. So it's clear that hard scattering observables are very sensitive to soft glue effects. They typically originate from boundaries of the phase space due to some unbalanced virtual and real radiation cancellation. And they generate large logarithmic corrections that need to be resummed, at least to some logarithmic accuracy, in order to improve or to save the conversions of the perturbative expansion. Typical examples are the low transverse momentum, when you get logs of transverse momentum divided by the invariant mass of the system, or the threshold logs that appear when your energy is just enough to produce a system with a certain invariant mass. And these logs typically grow very fast with the power of 2 faster than alpha S. So let me concentrate on very simple observables just to start with, which is a process in which you produce a color singlet object in the final state. So with CC bar, where C could be a quark or a gluon, that could be Drell-Yan Higgs, several gauge bosons, several Higgses, and so on, but colorless final state. So there are basically 2 extreme ways if you want to perform the resummation of these large logs, at least in the threshold case that I will concentrate in this talk. One of them is the analytical resummation, in which you arrive your cross-section by a combination of Born cross-section, some coefficients, but particularly the relevant part is that the logs are being resummed by introducing a pseudo-conform factor. So I put there one given expression for the pseudo-conform factor, which typically depends on two functions, A and D. These functions are free of large logs, so all the logs are generated once you integrate over this virtuality, this variable q squared in the pseudo-conform factor. And so therefore these functions can be expanded in alpha s, and the conversion to the expansion is expected to be good. The function A is very well known, is the one that drives the soft collinear emission, is given all the biorder in perturbation theory by the soft limit of the splitting function, and it's also known as the Kaspa anomalous dimension. So all the biorder in perturbation theory, this is exactly the Kaspa anomalous dimension. The other function D is the one that deals, for instance, with soft emission but non-collinear. Now, the other possible way and very useful way to resum these large logs, and of course to do much more in order to match the experimental conditions, is by doing a Monte Carlo. So just summarizing in one equation, in a Monte Carlo, you approximate your matrix element by assuming collinear branching, which is driven by the splitting function. And for instance, if you look at the probability of emitting a soft particle in the final state, it's given by the expression like it's shown there. It depends on the momentum fraction, the transfer momentum, and so on. But what is important is the soft and collinear emission, with the one that derives the double logarithmic accuracy, is completely driven by what is called the intensity of the soft gluon radiation, which at leading order is given simply by this color factor, Ci times alpha s over pi, where Ci could be Cf if the emitter is a quark, or could be Ca if the emitter is a gluon. This is a general feature. Now, how do you perform the resummation in a practical way in a Monte Carlo? The first thing is that in order to resum the soft collinear terms at leading log, what you do is you replace alpha s by the running alpha s with the coupling evaluated at the transfer momentum of the gluons. And in this way, you take into account, roughly speaking, a tower of emissions that gives the leading log. But if you want to go to the next leading log, which is what the Parton showers and the Monte Carlos achieved today, you have to do an extra correction, which is usually called the CMW procedure, in which you basically replace this color factor Ci by a function that has a correction at order alpha s. And this correction, which is given there by K, is very well known. It's just simply the Kaspa anomalous dimension at two loops. So basically, in this way, you take into account the soft gluon emission, including next to linear logs due to soft and collinear emission. So which is the main idea? The main idea is in this soft gluon effective coupling, which is depicted, shown in the right plot, if you want. You basically replace all the emission that is on the left side of this slide, in which you could have an emission of one gluon with one loop corrections, or two gluons, or a QQ pair. Everything is absorbed into the redefinition of this soft effective coupling, which takes into account those effects. So you have basically the same emission as at leading order, an on-shell gluon, but with a coupling which is being modified by this factor. Now, this is true up to two loops. This is very well known. The question is, given that at one loop and at two loop, this factor is given by the Kaspa anomalous dimension, and the Kaspa anomalous dimension is already known up to 4 loops, one might ask the question is whether this is going to be true also to higher orders. The answer is no, but in order to show that, the first thing you have to do is you have to do an all-order definition for this soft effective coupling. This procedure that put in this plot has to be properly defined to all orders. And that has been done by Banfi and collaborators in terms of what is called a web, very similar to what I showed in the previous slide. You take into account at a given order in alpha s, all the possible effects of emission from one given gluon with momentum k that could result into several gluons, QQ pairs, loop corrections, and so on. You compute this matrix element square, you integrate over the phase space of the final particles, and then you get a function, which is a web, that depends only on the momentum of this initial gluon, the one that will be attached to the emitter. It turns out that due to some invariance, this web depends only on 2 variables, which could be chosen as the transfer momentum of the gluon or the transfer mass of the gluon. Now, since you're going to replace all this emission by one single on-shell emission with a soft effective coupling, then you have to leave it in such a way that it depends only on one variable, which would be the same variable you use at leading order. And therefore, you have to integrate about one of these 2, or either KT or the transfer mass. Actually, you could choose many different possibilities, but I put here 2 extreme scenarios in which you integrate this web over the transfer mass, keeping the fixed value of KT, which is the first definition that was done by Banfi and collaborators. And this is what we imagine that will be suitable for QT-related observables. If you have a process which generates large logs of QT, that is probably a good definition in order to resum them. On the other hand, if you are interested in threshold-related observables, then you would integrate over KT, which is not the most relevant variable, and leave the unintegrated variable as the transfer mass. So these two possible definitions can be done. As you can see, I've been keeping this calculation in d dimensions, 4 minus 2 epsilon. In principle, this calculation is totally finite. You can compute it in 4 dimensions and you get a definite answer. But as you will see in a moment, it is actually convenient to keep this quantity defined in d dimensions. So let me just flash some results. Of course, if you do the calculation at leading order, just the emission of one gluon, both definitions of this soft coupling will give exactly the same. If you do the calculation at 2 loops, actually, sorry, at 1 loop, as you can see also on this figure, you will get a result that in 4 dimensions is exactly the same. And as I said, is given by just the cusp anomalous dimension. But when you go to look at the expansion in epsilon, and we did the calculation to all orders, but I'm showing here only the first 2 terms in the expansion, you start to see that there is a difference between them. So to order epsilon, epsilon squared, they start to differ. So which is the reason in order to compute this quantity in d dimensions? The main reason is that we have found a very interesting relation. And the relation is the following. It says that if you compute any of these soft gluon couplings with any of these definitions, you compute it in d dimensions, d equal to 4 minus 2 epsilon, and you replace epsilon by the beta function of QCD, what you find is the following, is that all definitions give exactly the same result. And not only that, is that this result is exactly the cusp anomalous dimension that you know from the splitting functions. What is particularly interesting about this point that we call the conformal point is that when you set epsilon equal to the beta function of alpha s, the running coupling does not run anymore in d dimensions. So it becomes like a conformal theory QCD. So proving this is complicated. We did it by using the expression from the pseudo-conform factor in threshold, but we believe that there could be other ways to reach this expression also in a different path. What is the use of this expression? I can show you just one result, how interesting this relation can be. For instance, if you replace epsilon by the beta of alpha s, since beta of alpha s is a function of alpha s, you put it, then you expand any of these equalities in alpha s, what you find is a relation like the one I show in the bottom of my slide. It tells you that the soft gluon coupling in any of this definition, which is on the left, is exactly the same as the cusp anomalous dimension, plus corrections, which are related to the epsilon or epsilon squared terms of the 1 and 2 loops previous results, okay? Since we have computed the previous results to all orders in epsilon, we can use that in order to obtain, without doing a direct calculation of the 3-loop effective coupling, the corresponding result for any of these definitions. And those definitions are shown here. If you look at the 3-loop result for AT, which is the soft gluon coupling that you would like to use in order to perform the QT resummation, we find that we agree with the result that was guessed by Banfi and company, but also, which is very important, that it's exactly the same result that was computed by Becher and Neubert almost 10 years ago in order to compute the 3-loop coefficient to perform the resummation to next to linear log. On the other hand, if you do the same for the threshold resummation, you obtain a slightly different result because at this order, the functions are actually different. And this is the coefficient that is shown here. It actually provides the full pseudo-conform factor for threshold resummation up to 3rd order. So you can do resummation up to next to linear log by using this quantity. Which is important is it takes into account not only the soft collinear effects, but also there is included a soft non-collinear contribution for processes like in which you produce a color singlet object only in the final state. Just to show the last slide, we have been a bit farther on this, and by also doing an analysis on the pseudo-conform factor to the 4th order for loops, only for threshold resummation, we have been able to find the 4-loop expression for the soft effective coupling for threshold-related observables, and I just put there the numerical expansion. You see that starting from order alpha s to the 4th, the result is slightly different for quarks and gluon because the Kaspa anomalous dimension does not fulfill the usual Casimir-naive relation. So what I think is important is that it takes into account the full soft radiation from 2 hard partons in a color singlet. So this measures exactly which is the intensity of the soft collinear radiation from a given parton. It's exactly known up to 4th order for threshold-related observables. Of course, if you want to look at processes which are more involved, in a sense that you have several hard partons, the situation is more complicated. You need to take into account also soft wide-angle emission and collinear radiation, but still, this soft gluon coupling is not effective. This really measures which is intensity of the soft collinear radiation from a given parton. So I just finish here because my time is out, presenting my results. I provided the definition of the soft gluon effective coupling at higher orders with explicit results for next to leading order and even to NQ below for threshold-related observables. And we found this interesting conformal relation to all orders that we believed has interesting use for the future. Thank you.
Thank you very much, Daniel, for this nice talk. And are there questions from the audience? So I have a quick question. So do you think that these effective couplings can improve the resummation precision of Monte Carlo programs, basically go beyond next reading log?
Yes, of course, as I said, that is enough if you look at color singlet production process. If you want to look at sets or something like that, then you have to complement with the effect from the final state radiation, soft exchange between different particles and so on. But this is the first step if you want in order to improve the accuracy of the Monte Carlos.
Very good, thank you. Any more questions for Daniel? Okay, I think we can move on to the next talk. Thank you very much.
Thank you.
And the next speaker is going to be Krasimir Komariki. I'm sorry if I mispronounced it. Revealing proton structure with neural networks. Thank you.
Okay, let me try to share. Does this work?
Yes.
Okay, so I'll be talking about revealing proton structure using neural networks, and I will shortly introduce first this field of study, which is studying the proton structure using generalized parton distributions, and then I will use this to investigate some more physical properties of proton, like quark pressure inside of it and distribution of different flavors inside of the proton using parameterization of GPDs by neural networks. So basically what we are doing, and we are trying to find out as much as we can about how the partons, quarks and gluons, are distributed inside the hadron, and leading most general function would be like an amplitude for a proton to emit a parton with a given any form momentum, and then reabsorbing a parton with different form momentum. Unfortunately, such function is not available experimentally. We cannot access it. Nobody has found any way to access such functions. So what one does, one throws away information which is inaccessible, either by integrating over inaccessible information or setting some kinematical variables to 0. And so one is progressing in such a way down this family tree of Hadron structure functions and ending with well-known elastic form factors or PDFs, which you are very familiar with. Now, the object of this particular study are GPDs, which are placed up here, which I would say is a sweet spot of this family tree, because GPDs are more powerful in the sense that they contain much more information than either PDFs or form factors, so to speak. But on the other hand, at the same time, they are also experimentally accessible in several different processes, and most convenient and most studied of these is deeply virtual Compton scattering, where it is done via laptop production, where you have a deeply virtual photon scattering of proton, and in the end state you will have photon and proton. And this process will interfere with the so-called Bethe-Heitler process, which is well understood, so you can actually use interference of these to get some additional handle on your hadron structure. So it is known that this DVCS factorizes into the convolution of so the form factors which describe the cross section, and they are at the leading order. There are 4 form factors. We denote them as H, calligraphic E, calligraphic H tilde, and E tilde. they depend on several kinematic variables, where this psi is related to x Bjork, and t is momentum transfer, and q square is the usual q square. So these form factors factorize into a convolution of the GPD itself and a perturbatively calculable coefficient function. So this is completely analogous to, for example, F2 factorizing into PDF and a similar form function. So coefficient functions. So these are known, and why we study them, why they're so popular? Well, I will just mention three classical objectives of GPD studies. First being the famous G-sum rule, which tells you if you knew the GPDs, you will essentially have solved the proton spin puzzle, because this first moment of GPD, this combination of GPDs gives you the longitudinal, total longitudinal momentum of a given parton species. Then knowing GPDs, you could actually make a Fourier transform and have a tomographic 3D picture of your parton distributions. So not only longitudinal distribution in longitudinal momentum, what PDF give you, you also have distribution in the transversal plane, and you have all the correlations there. So this is also very nice. And finally, what is maybe recently came to the fore of the focus, and which will be a subject of my talk also, is the pressure distribution in the nucleon. This is directly related to the subtraction constant, which occurs when you do a dispersion relation analysis of the Compton form factor. So this is related to something technically called GPD term, and these relations are sort of simple. So the pressure distribution is kind of simpler than the two guys above, because you can get to it by only knowing the Compton form factors. You don't need to deconvolute this formula and get to the GPD. So already knowing the Compton form factors would be enough in some sense to measure the pressure distribution. So this was really interesting, and a lot of people calculated this D term or the subtraction constant in several different models. This is some summary plot here. But question, and there are also lattice QCD calculations of this object, but interesting questions, of course, can we measure it in the nature? So 2 years ago, a group of people from the class collaboration from JLab actually used their DVCS data to extract the D term with great precision. These are the small purple points here. So they were able to essentially measure the pressure of the quarks in the proton that was published in the Nature, caused a lot of stir. Now, these people used the model for GPDs and Compton form factors that was developed by Dieter Miller and myself some years ago for general fits, and we were kind of aware that in our fits we were not really sensitive to this D term. As you can see, left-hand plot shows you the imaginary age, so leading form factor coming from different choices of model, different fits, different data. So it's really very stable. However, we kind of observed that we can get really different values for this D term, and that is in the end for the pressure, depending on details of our studies. So I'm trying to now, I will present to you a study that we try to fix this situation somehow to get an assessment of how much of this is really model dependent, and how much is really there in the data. So to fix this systematic uncertainty due to the model selection, we will use neural nets, because they are known to be good for fits, good to parameterize unknown soft functions. Actually, since this community is more in the, so to speak, PDF world, and you know that there is a well-known group of people in PDF who are doing PDF fits with neural nets. Here, we believe we have even more power when you use neural nets, because the functions that we are after depend on much more kinematic, either 2 or 3 kinematic variables, unlike PDFs, which depend only on X Bjorken, putting aside Q-square dependence, which is well understood. So we have more complicated functions, which are very poorly known. So choice of any fitting ansatz on the space of 3-dimensional, 2-dimensional space of over kinematics is really, really complicated, and you can introduce a lot of bias by choosing your ansatz. So neural nets are really nice for this. So we did that, and so this is the architecture of the neural net we do. So input is X Bjorken. This is actually the psi on previous slides, and this momentum transfer T. and then output will be our Compton form factors, or in the future, hopefully the GPDs themselves, and the subtraction constant of the dispersion relation, so that we can actually use dispersion relation to get the real part of our Compton form factors. I remind you that there are 4 of them. So we will have like 8 functions that we are after, 8 real functions. So now we use this parameterization of the Compton form factors and fitted it to the same data set as the class people did. So it turns out that we were able to get a good fit and to all the data that was used. And well, when then this transformed into some knowledge of actual form factors, for this imaginary age is the leading form factor, and knowing of both imaginary and real part of age is enough for this pressure measurement. Now, imaginary age is kind of stable. So you can see the red band is the result of this Nature paper by the class group, and the blue and the green bands are our results by the 2 different choices of number of Compton form factors that we use for our fits. So for the imaginary age, we get a really stable result. Everything is nice, everything is known. However, for the real age, it's not, we get some disagreement. We have different absolute value, and we have a quite large uncertainty, especially in this important region here, where the data is. So this doesn't look maybe so much of a larger discrepancy on this plot, but however, when you turn it into a number for the D term and for the pressure, you get something that is consistent with 0. So the result is that actually the procedure itself is valid and it should be used, and probably in the future with more precise data, we will be able to measure the pressure in the proton. But at this point, we still need to have a model-dependent assessment of the pressure. And if you really throw away all the model ideas and go really unbiased with neural networks, you will get 0. So this is the result. And also this was confirmed also by other group of people who also did, this is a Parton's group who did does the same thing. They used global DVCS data, slightly different choice of parameterization, but again, the D term and this subtraction constant, this gain is consistent with 0 throughout the kinematic region. So this is like sort of a bad news. Now, the good news, we have now also tried to improve that. We made a global fit to all JLab data. And what we got first is here in the recent paper, we were able, out of these 8 leading Compton form factors, using this data, we were able to extract reasonably 6 of them. So this imaginary age is here again. You can maybe concentrate on the green ones. These are more theoretically firm, so to speak. So the green bands is here. So the real age, this already you have seen. Now it's a bit more precise with more data, but also now E, Compton form factor E related to GPD-E. This is really important one because it is directly related to this G-sum rule. So in the future, it'll enable the solution of the proton spin problem. So now this is, I would say, maybe the first clear extraction of this E Compton form factor, and also H tilde, polarized one. This is one related in the forward case to the polarized PDFs. So it also comes out okay. And this imaginary E tilde. The 2 additional real part of H tilde and real part of E tilde, we are not able to extract. They are consistent with 0 for this data set. Now, this is only, I mentioned this is only moderate valence ex Bjorken, so what is accessible with JLab data. We did also previously some fits to the HERA data, which got us this age also for in the small X region, but I chose not to present this here. These are somewhat older results. Now, a very interesting final result, which I will show at the end, is what happens when, now this extraction here is completely by using the proton DVCS. Now, since this is a photon scattering, photon, of course, is flavor blind, so you cannot get anything about flavors, particular separation of flavors. However, adding neutron data helps, and there is a really nice measurement of the neutron data by Whole A collaboration, which was published this year. So we added this neutron data and into our fits, and what happens, so on the left-hand side, you can see total fit to the proton DVCS. These are the red dots, and the neutron DVCS, these are the blue dots. So fits come out nice. This is not all, I mean, there are several hundred data points. I'm just focusing on these neutron proton measurement by Whole A here, but when taking everything together, you get result on the right-hand side, further to the right. So the right-hand two panels are showing imaginary age and real age, so the leading quantum form factors, where you have a red band showing the distribution of the U quark and the blue band showing the distribution of the D quark. So you have a really nice separation in this is depending on the momentum transfer T. So Fourier transform of this would essentially give you some sort of a distribution of separate for U and D quarks in the transversal dimension in the proton. This is sort of like a final result that I wanted to show you. So of course, when you are separating flavors, the uncertainties are larger. As you can see here, when you add this U and D quark, then you get left-hand plots, which are the green bands, which are just total quark contribution, which is then the uncertainty is of course much smaller. So this is the final result, and I want to summarize that I try to show that neural network method has a unique capability of extraction of quantum form factors, and we hope in future also GPDs and reliable uncertainties come out of these studies. We need more experimental work to really determine this pressure distribution in a reliable and model-independent way. And when you take proton and neutron data together, you can get a clear separation of U and D quark flavor contributions to the leading quantum form factor. So thank you very much.
Thank you very much for this talk. Are there any questions from the audience? Okay, I have one question. I was actually curious to know if you combine these sophisticated methods, neural network methods, with the anticipated precision from the future EIC, yes, how much improvements do you think we will get as far as understanding the proton structure is concerned?
Well, we are just sort of in the middle of such studies. We did some studies of EIC impact on the model-dependent fit some years ago, and already there you could see you get some idea how much EIC would be valuable to the community. As far as I know, nobody has yet really applied neural network in these GPD studies to pseudo EIC data, but we have studies, ongoing studies that, so we will have this soon, I hope, to really, because everybody's interested really to measure the impact of the EIC, and right, it should be really good, and but no exact studies are available yet.
Okay, thank you.
Thank you.
And if there are no more questions, we can move on to the next talk. And the next talk will be by Ritu Argawal on dedicated data analysis for improving PDFs, study of proton pattern distribution functions at high X and charm production in charted DIS at HERA.
Just a minute.
Sure.
Okay, so this is a Zeus presentation. I'm presenting here two dedicated data analysis for improving PDFs. One of them is study of proton pattern distribution functions at high X, and the other one is this charm production in the charged DIS HERA. Both of them have been published. The one on high X have been published recently, and the charm in the charged current DIS was published last year. So on the next slide here, I would bring a small overview of the Zeus detector at HERA. Both the analyses are done on the HERA-2 runs, which was from 2002 to 2007, which had increased luminosity and improved tracking system. So on here, I will start with the first analysis in the order, that is the HiX data analysis, and I will try to bring out the motivation of studying the published Zeus HiX data. The data I'm talking about was published in 2014. A link is given at the bottom. Now the top at the left here is taken from this paper. And so why this data is special? Because as we know, the Zeus data that have been included in the PDF fits is only X up to 0.65. A plot on the left hand side here shows a comparison of the legacy high Q square Zeus data in the blue points, sorry, in the red points, to the HiX data that I'm talking about in this presentation in the blue points. And we clearly see that HiX data spans larger, higher values of X at high Q square. Now this data is neutral current, and here I'm showing an event display from a neutral current event in data. And so these events, which are really the HiX events, which span up to very large values in X, these are very clear and beautiful events in which the jet reconstruction is not possible. But we know that these events have value greater than X, some X edge, and we integrate all those events in a given Q square bin, and these are what these points are. So often at these points, the number of events expected are small. So the reconstructed events are small. And that's why this data have Poisson errors quoted on them in the paper. And of course, this has a subset to high Q square data as discussed, but HiX data spans larger kinematic X plane. So we have developed here a transfer matrix technique in which different PDFs can be used. And from those different PDFs, the expectation for the number of events reconstructed in data in the cross-section bins can be determined. So the equation here shows, starting from the cross-section at the bond level from a given PDF K, the events can be reconstructed in a given bin J can be determined using this equation. Now this equation is assumed or approximated with the matrix in a metric approximation like this, where the matrix AGI would take the expectation at the bond level to the reconstructed level. Here matrix A can be decomposed into two matrices. One is called as the transfer matrix and another is the radiative corrections here. Now this and in the vector form, this can be written like this. So here TJI would represent the transfer matrix, and each element will give a probability that an event reconstructed in the jth bin comes from the ith true bin. So here the definition of how to calculate it from the Monte Carlo is given, and I will talk about the plots here which are taken from the paper. So here the distribution of the events in the generated space is given. And when we convolute it with the T matrix, that is the transfer matrix, the expectation in the reconstructed plane can be attained. So using this, if we start from lambda, that is the bond level from any PDF, we can multiply it with the radiative corrections and then convoluted the transfer matrix, and the expectation for the events in the data in the cross-section bins can be attained. So this is the idea behind developing this technique. And now this can be then compared to the number of events actually reconstructed in data. So different comparisons have been made. Comparisons have been made at the generator level for the different from different PDFs that I'm going to show in the next slide. Now, comparison has also been made at the reconstructed level. By generating a probability of the given data, given the PDF K, the expectations from the K PDF calculated using the Poisson statistics like this. Now, having this probability from various PDFs, base factor, which is the ratio of the two probabilities, such probabilities, delta chi-square, calculated like this, and the p-values can be determined from different PDFs, and have a table showing the comparison of different PDFs, these values from different PDFs, and study of the systematics have been done, and the normalization uncertainty has found to be significant. So in this slide, I'm showing the ratio of the generator level cross sections in different PDFs to HERA PDF 2.0 and in LO. So here, what we should look at is the difference. So we are here talking about the high X region. So first thing I would like here to show is that the linear scale in X, which shows the really high X that we are talking about. And then the differences at the high X. I mean, the differences between the different PDFs with respect to HERA PDF 2.0 is quite large. Now here in gray area is the PDF uncertainty from HERA PDF 2.0. Also shown for comparison is NNPDF 3.1 uncertainty overlaid over the HERA PDF uncertainty, and clearly the ratio at high X goes far away from the expected uncertainties. So on the next slide here, I'm showing here the p values p1 by p2 and delta chi-square, these values from comparison of different PDFs at the reconstructed level. So here, if let's talk about the p values, we see different trends in E plus and E minus data sets. So p value for HERA PDF, let's say for E plus P is lower than other PDFs, whereas for E minus P data set, it's better. So if we divided the data set into lower and higher X region, where higher X would mean highest 3X points in each Q square, we'll see the conclusions don't change much. So with this, I think I will move to the next analysis and conclude maybe together in the last slide. So here, I'm presenting the second analysis, that is the charm production in charge current DIS at HERA. The motivation of the analysis is to probe the charge content of the proton via a charge current interaction with the C quarks or C gluon. The interaction that can place are shown on the left-hand side. The bottom row are the interactions with the gluon. The electroweak process of interest is process 1, in which the interaction is via a strange C quark and a charm quark is produced in the final state. Also, as shown in the right side bottom, there could be an interaction with the valence quark where charm quark is produced from QCD radiation in the final state. This QCD part has to be subtracted from total visible charm cross-section to get electroweak part of the charm production. So one more aspect of studying the strangeness of proton, that it itself is a model-dependent quantity. So here are given some of the cases and showing the charm fraction, the strange fraction in the proton. And also shown are the experiments that favor them. So also the various processes and the kinematic region where they are relevant depend upon the DIS scheme used. For example, in a fixed flavor number scheme, no charge content would be there, and the process labeled as 2 in the previous slide will not occur. Instead, there will be a larger gluon content. So having said that, here on the top left, an even display of charge current EP interaction is shown. These are the events with missing lepton information in the final state, due to which hadronic information has been used to reconstruct the kinematic variables. As shown here, the control plots on the right-hand side show the event properties of the events that pass the charge current selection criteria. The blue line here is a charm signal Monte Carlo, and the red line is the light flavor Monte Carlo, which would be a background in this analysis. So next step in the charge is the charge tagging, which is done by lifetime tagging method. In this method, the jets with more than 2 good reconstructed tracks, as shown, the control plot is shown here. More than 2 good reconstructed tracks are fitted to obtain a secondary vortex. The underlying principle of charge tagging here is that the heavy flavor particles would travel a measurable distance before decaying, whereas light flavor will decay promptly. The transverse decay length of the secondary vortices will be symmetric with respect to the primary vortex, whereas for heavy flavor, it will be asymmetric. So it is shown here, like for the blue, it is slightly asymmetric. It is, and for this light flavors, it is symmetric. Therefore, the light flavor background can be subtracted by, can be suppressed by subtracting the negative decay length from the positive. So the control plots here on the right side show the distribution of the event decay length and the significance of the decay length. The middle row shows the light flavor suppressed charm signal. So the surviving events after the decay length subtraction were used to extract the charm cross section in 2 bins of Q square. The lifetime method tags charm events irrespective of their origin. So moreover, limited statistics prevented an experimental separation of different theoretical contribution. The visible charm cross section is shown in top row for E plus and E minus data, and the extrapolated electroweak charm cross section is shown in the bottom row for the 2 data sets here. And also shown are the expectations from different schemes here. So here now I will conclude for both the analysis, starting with the first one, high X analysis, that the transfer matrix building technique for the Zeus high X data have been shown. It can be used to predict the number of events in the cross-section bins. And it has shown ability to discriminate the different PDFs at the high X, where I have shown the base factor p-values from different PDFs calculated and shown on the basis of their explanation to the high X data using the transfer matrix. Differences have been seen in E plus and E minus data sets, as well as for higher and lower X ranges. So in the next slide, I'll conclude the second analysis, where the electroweak charm production has been measured for the first time in high Q square charge current DIS EP at HERA, which has been found consistent to be consistent with theory, though it is definitely statistically limited, and more statistics will be needed to investigate the strangeness in proton, which could be possible in future detectors with higher luminosity, better techniques for vortex detecting, and improved theory calculations. So thanks.
Thank you, Ritu, for this nice talk. Are there questions? Yes, I see someone. It's a raised hand from Anton Stepanov. Go ahead.
I might have a question about slide 12. So here, as I understand, you're trying to enrich your sample with jets originate from charm quark by applying the cut for significance, right?
Sorry?
If I understand correctly, you apply the cut on significance to increase the number of events with charm jets, right?
Well, applying the cut with significance would reduce the sample size, but definitely it has been applied to increase the purity, in the sense the events with S less than 0 are the events which are very close to LXY close to 0, and these are large number of events. I mean, so to get rid of the, to reduce the statistical uncertainty, this has been used.
Okay, and then you subtract the number of events which are not charm from Monte Carlo after applying this cut and subtract these events from the data, right?
So I don't understand the question. I mean, after applying, so the distribution from LXY positive has been, I mean, the negative has been subtracted from the positive. So the number have been subtracted.
Yes, and in the end, you have a sample with some number of charm events, which is signal, and some number of light and other events, which are backgrounds, right?
Yes.
And then you subtract the number of backgrounds from the number of events in data.
Yes.
After applying the same cut. And my question is, do you rely completely on the Monte Carlo predictions for the number of background events after such cut?
So background have been checked, like the other backgrounds have been checked, which are neutral current background. And those have been found to be, and also from photo production, those have been found to be negligible. And so here, the very small beauty background was considered, which again is found to be negligible after subtraction. Yes, but small, these events have been there, yes.
I see, thank you.
We have another question from David Danteria.
Hello, can you hear me?
Yes.
I maybe missed something because I could not connect the whole time, but if you, in slide 13 again, how come the cross-section is negative? How can this be? Why do you, I understand that you subtract some background, but you should have a lower bound at 0, no? I mean, how can the negative charm be negative?
So
I don't understand.
clearly this is statistically limited.
Yes, but it cannot be, a cross-section cannot be negative. Why don't you bound it to be positive?
Well, I mean, I don't have any answer to that, but yes, I would say that the data is statistically limited, and bounding.
So tell me what it means. A cross-section is -2 picobars. What does it mean? Or -5 picobar for the second Q square in the bottom right plot.
I mean, the error bars are large.
Yes, but the central value cannot be negative, no?
So this means 0.
Yeah, that's what I'm saying, that you should, I mean, they should have bound this to 0. And okay, I was wondering if I had missed something. Okay, thank you.
Okay.
Okay, any more questions? It doesn't look it, so we should move to the next talk. Thank you very much.
Thank you.
So the next talk would be by Agnieszka Kudzak, who will talk about investigation of high energy behavior of HERA data.
Hello. Maybe I will try again to share my slides.
And if not, I think the host can share them if you wish. Should we try the host? Because we really have a tight schedule.
Yes, yes.
Okay, I will share the slides.
Thank you.
Can you see it?
Yes, I can see. Thank you.
Okay, so just please tell me when to switch.
Okay.
Can you speak louder, please? It's very hard to hear you.
Okay. Now it's better?
Yes.
Okay, so I will tell about investigation of high energy behavior of HERA data. And next slide. Next. We analyzed the high precision HERA F2 data in the low X region, X less than 0.01 and very low X less 0.01 regions using lambda fits. Lambda is a measure of the rate of rise of F2 defined by this formula for F2. You can see in blue color, so F2 is proportional to 1 over X to the power of lambda. And we show that lambda determined in these two regions at various Q-square values is systematically smaller in the very low X region as compared to the low X region. And we discussed some possible physical interpretation of this effect. The analysis is based on this publication. Next slide. So now I would like to tell a few words about description of fits. So as I mentioned at my previous slide, we determined the lambda parameter from a fit of the function F2 equal A multiply 1 over X 2 power of lambda, and we did the fit to the final high precision H1 and Zeus data measured at HERA. Here A is a normalization constant dependent on Q-square. And the fits are made in two range of X. As you can see, it is low X region, and for each Q-square value separately with 0.3 less than Q-square and less than 250 GeV. And the final data are given as reduced cross-section, which is connected to F2 and FL by this formula for sigma red, which you can see in blue color, and Y denotes the inelastic parameter in the selected kinematic region, and contribution of the structure function F3 can be neglected. And following the discussion of properties of FL in the H1 paper, we assume that FL is proportional to F2. This is also in agreement with the Zeus result. Next slide. So we have then F2, formula for F2, which is, as you can see in blue color, sigma. Sorry, I don't have pointers, so I just say that my formula is in blue color. So you have a sigma reduced divided by this part where we have also R. R is a ratio of FL function divided by F2 minus FL. And the evaluation of FL shows that the ratio R is only weakly dependent on X and Q square, especially in the kinematic region of the present investigation. So Y is less than 0.01 and is greater than 0.1 and less than 0.8. Thus, we assumed R equal 0.25 in agreement with data, the QCD digital predictions and the dipole models. Next slide, please. Now I would like to show you results of fits. So this is first table which shows the values of lambda constant with its error for two low X regions, X less 0.01 and X less 0.001. The fits are of good quality as the average value of chi-square divided by NDF is 1.05 at X less than 0.01. Next slide. In table 2, I'm showing the values of A constant and its errors in these two kinematic X regions, as you can see on the top. Next slide. So now I would like to show my pictures. So the first one shows the power lambda as determined from the fits in the X less 0.01 region at all accessible Q square values from table 1. The next figure is on my next page, please. So on this picture, you can see comparison of the results of the lambda fit in the low X, so X less 0.01 and very low X, X less 0.001 regions. And these are red points. And the black are for the first region, and only points determined with differing data are shown from table 1. Next slide, please. Okay, so now I would like to show a few pictures starting from F2. Starting from Q square equal 2.7 GeV and 3.5, and this picture shows the fitted curves for F2 formula. So F2 proportional to 1 divided by X to power of lambda, and I'll show the fitted curves. We have here two fitted curves. I'll show together with the data at indicated Q square values, as I said. So the full line shows the fit in the range for X less 0.01 and dotted line in the range X less 0.01. Next slide. So in these plots, we compare the fitted curves to the corresponding data for Q square equal 2.7 and 3.5, and the curves are drawn with the value of the constant lambda and A given in table 1 and table 2. The full line, as I said, show this the first region, and dashed is for the very small X region. And the curves, I will show now a few more pictures for different Q-square range. And all the curves are drawn in a larger region than the fits are performed to show the systematic difference between them. Next slide. So here you can see Q-square equal 4.5 and 6.5. Next. Next slide. And here is my fit for Q-square equal 8.5 and Q-square equal 10. Next, please. And now for 12 and for 15 GeV. Next. Next is for 18, as you can see, and 22. And next is for 27 and for 35. Next, the last one, please. It's Q-square equal 45. And now, please next slide. So in all plots, we compare the fitted curves to the corresponding data in Q-square regions between 2.7 and 45 GeV. The figures show quite clearly that the dashed lines are almost always below the full lines in the region of very small, very low X less 0.001. On the opposite end, around X equal 0.01, the full line is almost always above the dashed line. Maybe you can back one slide. So here you can see that's this effect that I told. On the bottom of this picture, you can see that the solid line is below this dashed line, and on the top is the dashed line is below the solid line. Please, next slide. And this is my last picture. And this is plot which show difference between the values of lambda determined in the low X and very low X region. And the black dots show the results for R equal 0.25. The triangles pointing down show the results for R equal 0.2, and the triangles pointing up show the results for R equal 0.3. And the arrows of black dots were obtained from this formula. Please change slide. Okay, so this is my summary. So we have confirmed that the simple phenomenological function F2 proportional to 1 divided by x to power of lambda fits very well the high precision HERA data in the low X region, X less 0.01 at all Q-square values between 0.3 great Q-square is chi-square, sorry. q square is greater than 0.3 and less than 250 GeV. Moreover, we have shown that this is also true for the very low X region, X less 0.001. And the new result of this investigation is that the rate of with lambda determined in the two regions indicate that lambda is systematically smaller in the very low X region as compared to the low X region. For Q square, greater than 6 GeV squared. This result is obtained due to high precision of the HERA data, and the previous earlier investigation conclude that the power lambda is not dependent on X within the experimental errors. This observation may indicate the onset of BFKL behavior in the very low X region, X less 0.001 and Q square greater 6 GeV. And it is in agreement with the analysis of Henry Kowalski, Lipatov and Ross paper. Our observation indicates, I believe, that measurements at the future electron-proton colliders like LHEC or VHEP will become exciting as they will approach the high energy limit of the virtual photon hadron cross-section where DGLAP and BFKL meets and the confinement effect should become simple. Thank you for your attention.
Thank you, Agnieszka. Are there any questions for the speaker? I don't see raised hands so far. In this case, thank you once more, and we can move to the next talk.
Thank you.
Can the host stop sharing? Thank you. So the next talk will be by Sarah Taheri Munfared, who will talk about TMD densities at leading and higher order from the pattern branching method.
Can you see my slide?
Yeah, we see them. Thank you. Go ahead.
Thank you for giving me the opportunity to speak at ICHEP conference. We just quickly recap the idea of pattern branching method, show what we have from the 5-flavor TMD at next to leading order and leading order, together with the next to leading order 4-flavor results, which we obtained recently. At the end, one of the application of this transverse momentum dependent distributions will be shown. We show the application of the pattern branching TMDs to Z plus BB production and compare 4-flavor and 5-flavor results. This is just the basic equation for this pattern branching method. We can rewrite the standard evolution equation in the form including the Sudakov form factor. Then we can write it in the integral form, which has a very simple intuitive physical picture. The first term here is just no branching probability, and the second term is where all the branching coming to the game. So this is just the basic idea of pattern branching method that one can solve the evolution equation with the iterative procedure. And since one has a sort of step-by-step individual branching, one can calculate all the kinematics exactly. We can make an association with the scale and physical quantities. We associate the scale with the transverse momentum of the emitted parton. Then one can say this is just the transverse momentum directly, or can say that we assume something like angular ordering, then the scale is associated with the transverse momentum modified by 1/1 minus z. Now, the question is, how can we determine parton distribution from data? First, a kernel is determined from the Monte Carlo solution of the evolution equation for any initial parton of flavor B evolving to the final state parton of flavor A. Then these kernels are folded with the starting distribution, the starting non-perturbative distribution. These kernels include the full parton evolution with pseudo form factor and the splitting probabilities, and they are determined from the parton branching method. We just use the full HERA1 plus HERA2 neutral current and charge current data from Q squared of 3.5 to 50,000 GV squared. And this is the standard kinematic range. The next two leading order results as already published. And this is the value of chi-squared over DOF. Set 1 is just the standard HERA PDF set with the scale in alpha S being equal to the evolution scale. And we reproduce, of course, the results for HERA PDF and for set 2, which is the interesting set. This is the set where we have the scale in alpha S changed to the transverse momentum, not the evolution scale. And here we have the parton distribution, the Geleon and C quarks for different Q squared scale of 3 GV squared and Z mass squared. And you can see that they are very different at the starting scale. Then here we have the results for leading order. PDFs derived at leading order are of special interest for Monte Carlo event generators based on leading order matrix element plus parton shower like MadGraph, Herwig, and also Cascade. And the leading order TMD is an important ingredient for the leading order multi-jet merging. And the value of chi-squared over DOF is a bit larger than next to leading order, which makes sense. And here we have our results for 4 flavor. In 5 flavor scheme, we just treated heavy quarks in the initial and also final state, the same as the light quarks, but by just ignoring their mass in the evolution of the matrix elements. In this picture, the heavy quark acts as an active quark in the QCD evolution equation and therefore can be founded in both initial and final state. On the other hand, for some processes, for example, for the production of Z or Higgs boson in association with B quarks at the LHC, the effects of the finite heavy quark mass become important. And in such cases, these quarks must be treated as fully massive. So they are allowed to be only in the final state. So this is our result, value of chi-squared over DOF. And here, I just show you a couple of plots to illustrate how well we can describe data with the 2 sets for these 3 scenarios, 5 flavor next to leading order, and 4 flavor next to leading order for both set 1 and set 2. Now, what do we gain with exclusive evolution? Here, we just compare the PT spectrum of Geleon between leading order and next to leading order. The blue one is next to leading order and red one is leading order. The difference between These two sets are coming from different starting distribution and also from the evolution. It's not just the difference in the starting distribution. It's an important message. We have it checked that if we use the same starting distribution, still we get these differences. So it has to do with the evolution with alpha S. At a small KT, this is essentially the starting distribution because we have no branching at the small KT, while at higher KT, we have more splittings, more branchings, and there is little difference between leading order and next to leading order. And here we have a comparison of Galon PT spectrum at 4 flavor and 5 flavor. At the small x, the blue one is 4 flavor, and we observe that at the small x and also small KT, 4 flavor is larger than 5 flavor due to the fact that it splits into a smaller number of QQ bar pair. And then to really see the difference between 4 flavor and 5 flavor scheme, we need to go to the LHC energies and look at the Z plus B and Z plus BB bar processes. Then here I will show you a simple application of the parton branching next to leading order TMDs at both 4 flavor and 5 flavor scheme to describe the production of a Z boson and B jets. Here we have the PT spectrum of the Z boson, and while we have at least two B jets in red, we have matrix element calculation at 5 flavor, which is Z plus 1 jet next to leading order, and in blue we have matrix element calculation in 4 flavor, which is Z plus 2 jets next to leading order. And one can see both 4 flavor and 5 flavor can well describe the measurements. Okay, here we look on the delta phi between 2 B jets for 5 flavor. In yellow, we have the LHC file, which is completely unphysical because it's not a full calculation. We just keep it for comparison. Then in green, we have TMD by generating initial state KT. The distribution from TMD alone does not really change much because with TMD alone, we do not get an additional B. The B comes from the initial state shower. So the difference between the yellow curve and the green curve is very small. What changes the distribution is adding the space shower, which is of course also clear because we are now looking for 2 B jets, and there is the initial state parton shower, which plays a significant role. And then we can see additional part here. We can see that adding the final state shower plays a role in the small delta phi region. And then here we have a very nice comparison between prediction for Z plus BB bar calculated in 5 flavor and 4 flavor scheme. And LHE prediction is shown in blue in both cases, while the full calculation is shown in red. Then on the left, we have a 5 flavor scheme. So there is quite a lot contributing from the TMD and initial state shower and also final state shower. While on the right plot, we have 4 flavor scheme, and we observe that it is essentially the matrix elements which plays a role, and we have rather little contribution from TMD and parton shower. Here we just considered 4 flavor and 5 flavor results, including TMD plus initial state parton shower and final state parton shower. And the interesting point is that at the end, both calculation for 4 flavor and 5 flavor do agree. And it would tell that the calculation, which involves TMD plus parton shower, is done in a consistent way, such that it would, at the end, it would agree with the full matrix element calculation. And this brings me to the conclusion. The parton branching method is a very powerful method to solve the Diglab evolution equation. It has the advantages that one can study the angular ordering condition. And here we describe the production of a Z boson and BB bar jets at next leading order with 4 flavor and 5 flavor scheme. And well description of this measurement is done by both schemes. And thanks for your attention. Just you are invited to connect to this link for more discussion after this session with the same password, Zoom password. Yeah, it's all.
Okay, thank you very much for this talk. Are there questions for Sarah?
No.
Can you go to slide 8?
Yes. Mm-hmm.
So you have this statement that says the uncertainty is smaller at leading order compared to next reading order. Yes. Can you clarify what you mean by that? And if this is really the case, why is your uncertainty at leading order smaller than the next reading order? That's not what you typically expect.
Yes, I will explain it. Just have a look at the Galois distribution here. Mm-hmm. We have these extra terms, but when we come to leading order, we just remove these extra terms because we just wanted to avoid having a negative Galois distribution at leading order. And I guess this is the main reason that we have smaller uncertainty here.
I still don't understand. So what is this extra term doing that you have at next reading order?
Here we have 3 more parameters for Galois.
Okay.
But this is at next to leading order. When we come to leading order, we just use the format that's also used in HERA PDF. And this is just to avoid having a negative Galois distribution at leading order. And then when we have less parameters, we have smaller uncertainty.
Yeah, I understand that. Yeah. Okay.
Yeah.
Okay. Are there any further questions? If not, thank you again, and we can move on to the next talk.
Thank you.
And the next speaker would be Mark Saddon, who will talk about determination of the parton density functions of the proton with the ATLAS data.
Hi. So just let me share my screen a moment. Okay. So hopefully that should be working.
Not yet full screen. Okay. Perfect.
Yeah. Okay. So I'll be giving a presentation on the Proton PDF from W plus JET data on behalf of the ATLAS collaboration. My name is Mark Sutton. I'm at the University of Sussex. So moving straight on to slide 2. So so why should we give a monkeys about the Proton PDF? Well, Claire gave a rather excellent introduction about this earlier on in the meeting. So on the right-hand side, for instance, you see the parton luminosities for gluon production. So right into the X region with the Higgs boson, you can see that the PDF uncertainty is rather large. It's either large or dominant. And in the other plots you see on the top left and in the middle, you can see some distributions for beyond the standard model searches. So there you can see the uncertainties really blow up at large invariant masses, which should come from large X, where the PDF is not so very well constrained. So of course you should give a monkeys about PDF, and that's what the rest of the talk will be about. So moving straight on to slide 3. So how we actually extract the PDF. So those people who may not be familiar with it, so the different sub-processes that you can measure at different colliders, they inform different processes. So for instance, DIS processes can constrain the quark distributions leading order with a gluon distribution through next to leading order corrections. At the LHC, the gluon and alpha S's can be extracted using jet data or top data, since they're directly coupled to the gluon distribution at leading order. But the rest of the talk essentially is for the things I'm talking about at the bottom there, which are electroweak boson production. And since the W and the Z bosons, they couple directly to specific flavors, then by looking at the different electroweak boson data, you can extract information about specific quark densities. And so, for instance, if you're looking at a W or a Z in conjunction with a jet, the fact that you've got an extra information, extra energy in the event means you can sample the PDF distributions at higher X than you would for the inclusive W and Z data. So move on to slide 4. So Atlas has a number of PDF measurements that we've made in the past. So there was this EPWZ12 fit that we did from the early 7TV data, and then there's another one, EPWZ16, which was again fit into the inclusive W and Z data but now with the full luminosity of the 7TD data. But we also had some W plus charm data, which is more difficult to fit, but we ran a profile of our previous fits on that to extract the fit. So since then, we've got this EPWZ top 18 fit, which includes the top data next to next leading order. All these fits are next to next leading order. So this the top data is the fit from the top data is just shown there on the right. So you can see the size of the uncertainties being very small, both for the X and D valence distribution at intermediate X. So moving straight on to slide 5, I think it is. I now noticed the plot is obscuring the page number. I apologize for that. So this is a discussion on the strange distribution, which we've already had some discussion earlier on in the meeting. So here, this in the previous fits that we saw, so Atlas saw this enhanced, well, not enhanced, but not suppressed strange, since the assumption has always been that basically the strange distribution is somehow suppressed and is approximately equal to half of the light quark density. So here on the top right, we now see the Atlas distribution from EPWZ. This is the strangeness ratio, as you can see there. And now we can see, if you look in green, you can see the actual full uncertainty that was not included on the CMS version of this plot, which when it should have been. So now you can see that as you go up to X at 0.1, the gluon distribution, the strangeness ratio can indeed go down a little bit as you go down. But the main thing to see here is that we're certainly not seem to be, at low X at least, we're not seeing this suppression that has previously been seen before. And it should be noted as well that this isn't an artifact of the fit that we're using. Since if on the bottom, you see the bottom 2 plots there, it shows that if we take the CTEC 14 and MMHT 14 fits, and if we profile that onto with this data, you see you also get with both of these PDF fits, you see an enhanced strangeness contribution. So it seems to be it's really coming from the data. So we have a new fit on the next page. Again, I can't see the page number because I've obscured that again. So apologies. So we have this new fit or newer fit where we've also included, as well as the inclusive W and Z data, include the W plus jets data. This is W plus W decaying to an electron, and we have distributions there for PT of the W and the PT of the jet, but we don't have the statistical correlations between them, so we can only fit one distribution at a time. We can't fit them both simultaneously. And so for this fit, with respect to the previous EPWZ fits, we've a few changes to make it more consistent with the top fits. So for instance, because it's an electron data, W to electrons, the previous fits were fitting combined electron and muon data, so it's combined into a single data set. Now we've uncombined them and we fit them all together so that we can more easily correlate the uncertainties between the W plus jets and the inclusive data. So if we move on straight on to slide 7, so now the numbers have shifted on the pages. Sorry about that. So this just shows the PDF fit parameterization that we use. So it's quite a full parameterization. I won't go into the details, but you can see in black the points that are the terms which we allow to be as part of our standard fit, and grayed out these additional terms which we allow to be varied independently if we're for measuring the model and parameterization uncertainty. So with all these various constraints that apply, we have a 16 parameter fit, and we use use a fixed strong coupling from the world average. And so I should say also as well that because we're using this slightly newer methodology, then the first thing we actually do is we refit the EPWZ data. So we redo the EPWZ 16 fit, but using the newer methodology with the uncombined data and the combined data as a check. So on to slide 8. So here we see the chi-squared distributions for the various fits. I won't go into the details, but the left-hand side one is this uncombined fit of the original data from the EPWZ. So this is a new fit of just the inclusive W and Z. Then we have the fit to the PTW, and then the fit to the leading to the PT jet. And you can see the chi-squares are all reasonably consistent there. Down this right-hand side, you see the chi-squares that we get from the variations of some of these additional parameters which we allowed to be free in the fit for the systematic uncertainties. So we use we pick, since the chi-square is slightly better and it's reasonably arbitrary, we pick the PTW distribution as our central fit, which takes us on to slide 9, which shows the actual fits to the data. In this case, we see both the fits for the EPWZ fit, 16 fit, and the new fit to the uncombined data with the PTW on the left and with the leading jet PT on the right. And there you can see with the bottom, you can see the ratio between the two, and the blue lines show the new fits, these two fits, and clearly they're much better than the EPWZ fit, particularly at large PT, which is essentially coming from large X or larger X. So on to the next slide, so slide 10, you actually see some of the PDFs themselves. So the first thing to notice is on the top right there, you see the gluon distribution. This is essentially unchanged. Although you are directly sensitive to the gluon at leading order for the W plus jet data, but the constraint is not particularly strong. So we still see the gluon distribution is largely the same. But we also see that the U and the D valence distributions are more or less the same. The UC is, the light quarter UC is almost the same, but here we do see an enhancement of the D bar C at larger X. So you can see in green with the large error bar, this is the original fit without this W plus jet data, so you can see how large that uncertainty is. But then when you include the W data, the W plus, the WPT data, which has a sensitivity at larger X, and this really constrains the uncertainty a bit more. And also it shows that the PDF itself at large, the D at larger X is increased slightly. So if you now move on to slide 11, so again, on the top left, you see the big plot again there. So now this is a strangeness ratio. So we don't show the strange density itself, but we do show the ratio. And there you see we have this big uncertainty coming at large X from the fit without the WPT data. But when you include the WPT data, you see the uncertainty is much smaller, and it also brings down the PDF a little bit. And of course, we have to remember this coming down is completely correlated with the increase in the D-bar distribution that we saw on the previous slide. So this is quite a nice show of how good the PTW data is for constraining the PDF. So onto slide 12. So here we see distribution for the light quark asymmetry. So it's D bar minus U bar, and this is on the top right plot there. You see again in green this big green band with a slightly negative. So the central fit, the dark green band, is actually negative at intermediate X, and this was always a criticism of the fit. They said that certain people were saying that because the only reason we're seeing the enhanced strange at low X is because we're constraining we have this this negative light quark asymmetry. But now with the new fit, we can see that we actually now get a positive definite, well, it's not positive, but we now get a positive D bar minus U bar distribution, which is much more consistent with the global fitters, which you can see on the next slide, slide 13, where you see on the right hand side, you see a plot showing the strangeness ratio for a particular Q squared, so Q squared of 1.9, GV squared, and X of 0.023. And there you can see this unsuppressed strange around 1. So in this band is the new fit, and then we have these the EPWZ is shown there in the middle with just slightly larger than the fit the new fit, and then we have the consistent fits for the constrained the combined and uncombined data. So that's all reasonably consistent. But then if you look down at all the global fitters, they tend to be slightly lower because they're making this assumption, or partly making this assumption of this this suppressed strange. And also you see on the plot, which you see in the blue points and the dark red points. So those are the results I showed earlier on of the profiled CT14 and MMH2 2014. So you can see they're both consistent with our new fit. And indeed this CT18A fit, you can see that this is a new CT18 fit with which includes the Atlas data on the Z production. So you can see there that has a significantly larger strangeness ratio of around 0.77, larger than the one without this data, which is a much lower value. So that already brings me onto almost the last slide, but almost the conclusions, the last slide before the conclusions, which are things that we have made available to the community. So the first thing there in the little orange box, that's the PDF itself that reporting on in this presentation here, the one I've been discussing. This is actually available to people in LHA PDF format by clicking on that link that says here. That will download a tar file which has the PDF for you. And in addition, the grids themselves that we use to calculate the next linear order contribution to the W plus JETS cross section, they can be downloaded from the Plowshare website. So there you can click on the links there as well. The K-factor also available, but not on the Plowshare website. But also recently, very recently, we have a new improved treatment of the luminosity uncertainty in the W plus JETS data. So that's just a table there showing the size of the uncertainty for some of them. I won't go into any details, but if you are interested in fitting this data, then these updated luminosity numbers would be extremely useful to you. So these are new things which we have made available, which now brings me on to my last slide, slide 14, which essentially is just to summarize. We have, so Atlas has this large and growing portfolio of precision measurements, which all have precision to constrain the PDF in quite a strong way now. So I've commented here on this newer fit of using the inclusive W and Z data, which is enhanced by the inclusion of the W plus JETS data. We have things to look forward to. So we already have this the Z plus JETS data, which is available. So there's a link to the paper, and there was a presentation from Camilla earlier on, which she gave quite good details about that data for anybody who's interested in it. And we will certainly be fitting that in the future. We have rich pickings still to be had from the full luminosity run 1 data, and even the run 2 data at 13 TeV still hasn't been fully exploited yet. And for many of the measurements we have been showing or discussing here, many things discussing here, the next order calculations are now properly available for new physics processes. And we have new technology, so these can be properly used in the fits. And so it'd be quite useful to see how that how we progress with that in the future. And certainly we've come a long way, but we're still only at the beginning of our journey towards realizing the full potential of the data. So it promises to be very interesting times ahead. Thank you very much.
Thank you very much, Mark. Any questions for the speaker? If you go back to slide 14, you had this nice break of sources of uncertainty, and it looks like jet energy scale and jet energy resolution are, the dominant, in my opinion, when you go to 1 or more jets or even higher jets. So what is the plan for improving these sources of uncertainties? Clearly, they will be having an impact in the future if they are reduced.
Well, there's Atlas has very recently published a very extensive paper on the jet energy scale uncertainty. So certainly for new measurements, we'll be looking at these uncertainties again. As always a good idea to try and reduce them, but a lot of effort has gone into understanding the jet energy scale and the various terms. So, and these have been used, but again, as I say, this is 8 TeV data, and we have all of the run 2 data to be analysed as well. So, so there's clearly a lot of things that we will be doing to understand the data a lot more with the newer data when we do the new analyses.
Thank you. And then on slide 9, there was this uncorrelated uncertainty statement. So what uncertainties are you referring to there?
This one.
Let me see. Yes.
Okay. So this is so basically, as I say, so these 2 fits are separate fits. So the uncertainties between the 2 fits are not correlated with each other. So these points here just show you the uncertainties, the uncorrelated uncertainties, not the correlated systematic uncertainties. They're not drawn on the points.
Okay, thank you. Any other questions from Mark? If not, we can move to the next talk. Thank you again.
Right, thanks.
Thanks. So the next speaker will be Mikhail Sambera, who will talk about isolated photon production and pi photon correlations in high energy proton-proton and proton-nucleus collisions.
Now, can you see my screen, please?
Yes, we do.
Okay, thank you. So, okay, but I cannot move my, okay, now, sorry. So why are we interested in isolated photon production? There are several reasons. We would like to study it, and we are actually studying it in PP and PA high energy collisions, which represent an attractive and clean probe in soft and also in PQCD regimes, as well as in nuclear effects and medium-induced QCD phenomena. Data on isolated photon production can be used to set constraints on PDFs in specific kinematical domains not sufficiently well explored by HERA, which is the focus of ongoing and planned measurements at the LHC and RIC. Also, at very low X, primordial transverse momentum evolution of incoming partons and nonlinear QCD effects such as gluon saturation start to play a significant role, whose reliable first principle analysis represents a long-standing theoretical challenge. There are just the two references, which are at the bottom, to the LHC and RIC experiments, which are planning to extend their capabilities in the forward region to access low X physics via photons. Let me remind you very old, well, almost 30 years old physics of color dipole, which will be used to analyze and predict the production of direct photons. This is based on the observation made by Nikolaev and Zakharov in 1999, that actually we can see the interaction of a virtual photon in DIS as an incoming quark, the anti-quark dipole. And Formula 1 shows that this that the cross section actually is an integral of the product of the wave function for splitting transverse or longitudinally polarized virtual photon into a QQ bar, and the cross section of that QQ bar dipole. There are different parameterization, but most well known is the assumption of so-called geometrical scaling, when you assume that this color bar, that this cross section actually is given by the ratio of dimensionless function, and this actually leads to prediction of the saturation and the saturation radius. So how do, there were, next slide. We have used in previous analysis color dipole model to analyze the production of neutron gold predictions at leading to the forward pions at RIC, also to predict the dilepton spectra for RIC and LHC in PP and PA, and also prediction of Z0 boson spectra. There is also paper on heavy quark production in proton-proton. The topic, of course, of my talk is based on the recently published paper about PPPA going to isolated photons. So what is the basics of the use of the color dipole model? I will illustrate it on this current analysis. So cross-section, of course, is always for producing prompt photon is Lorentz invariant, but its partonic interpretation is frame dependent. In the CMS frame, it occurs via Compton scattering, but if you go to the lab frame, it appears as a photon Bremsstrahlung of a fast projectile quark propagating through the low X color feed of the target. These are two diagrams shown here. On the left is when the photon is emitted after, and on the right, when the photon is emitted before interaction with the color gluon field. The nice thing of this approach is actually that if you stay in the lab frame, the lifetime of partonics fluctuation is enhanced with respect to that of the CMS. So effectively, it's accounting for the higher order PQCD corrections. So now, how do we calculate a cross-section of quark interacting with the target leading to the Q, gamma, and X final state? We have to assume that we are at the center of mass energies higher enough than some charm and bottom quarks, and then we take the amplitudes of the two processes I have shown in the previous slide. Then you produce the matrix element squares. You obtain some interference terms, and you obtain the formula with the yellow background, which is produced here, where you have the constituent quark masses, you have the light cone wave function of the real photon radiated off quark with flavor F. And there are also some other shifts, like transverse shift relative to the initial one, and rho is the transfer separation between quark and photon. On the next slide, I show how to plug that into the final formula of proton interacting with target, be it proton itself or nucleus. And this is our formula, which we will employ afterwards. So what we do now, we know the wave function for quark radiating the gluon, but we do not know the QQ bar cross-section with the proton. So this is done using three different models. One is the famous Golets-Biernaut-Wisow models, which led to the geometrical scaling. Second is the saturation model based on color glass condensate. And the last one is solution of Balický-Kovčegov equation with running coupling obtained by Albacete et al. And with the initial conditions constrained by a fit to the HERA DIS data. Now, for color dipole cross-section models application to nuclear targets, we have used two approaches. One is well-known Glauber-Müller approach, where we estimate all the multiple elastic scattering diagrams for the QQ bar dipole propagating through the nuclear targets. And the second one is the solution of running coupling Balický-Kovčegov equation for the nuclear case, which takes into account mutual interactions of the gluoning ladders exchange between the dipole and nucleus. So let me show the results of these model calculations. First is the transverse momentum spectra as measured by Phoenix collaboration at 200 GeV, 0.2 TeV, which are compared with GBW, CGC, and AAMQS. And you can see that all three models, more or less, maybe not CGC, describe data rather well. Now I will come, and it will be all of my rest talk only to the predictions. So predictions for 500 GeV for pseudo rapidity of in the forward direction the previous figure was at mid rapidity. Now I want to concentrate on the forward physics. So here we have on the slide number 11, pseudo rapidity 2 and 4. All three models are compared. On the slide number 12, I show prediction for the LHC at eta equal 4 and eta equals 6, which will be probably the reach of Alice focal project detector. And then also I will show, I'm showing on the slide number 13, the nuclear modification factor defined here in the yellow box for the square root of S energy per nucleon per 8.8 TeV. What you can see here is that actually there is a big difference between two GM and RCBK at the forward direction at eta equal 4. Now let me go to more discriminatory, at least I hope so, variable. well, with the increased luminosity at RIC and at LHC, we hope to be able to measure not only single direct photons, but also the associated production of pions, which are produced from fragments of the quark which radiated gamma. Here and on the figure, actually, I'm not showing the direct photon, I'm showing the virtual photon. This is the figure from work of Anastasia and her collaborators. Why I'm showing it is that in this paper and afterwards, they made a prediction that quark, in order to radiate the photon, he has to acquire its transverse momentum via multiple gluon exchanges with the target. When the target color field becomes dominated by low X gluons with about kT of gluons equal to the saturation scale, one expects that for transverse masses bigger or equal to the saturation momenta, there is a separation of gamma hadron correlations at 100 back-to-back degrees. So this was our stimulus to study azimuthal correlations of the virtual photons. And the formula I'm showing on the slide number 15 is valid both for virtual and also for the real photons. So this is how we define the coincidence probability per trigger photon. To describe interaction of the incoming quark with the target color field, we employ unintegrated gluon distribution function of this parameterization, where we also use the KKP fragmentation function of a quark with flavor F into a neutral pion, and we assume that the factorization scale is PT itself. So let me show you what we first observed for the off-shell photons, yeah, for dileptons. This is shown here for the comparison between proton nucleus at different momenta on the top, and below at the bottom are two figures from a paper of Stashto and collaborators. We have seen, similarly to her, that the away side double peak structure shows also in deuteron gold. We have seen also that independently on the factorization scale choices. So we concluded that we have to see the same phenomenon also in the proton collision. And that was really the case, which is shown on the slide number 17, where we show that in PP and also we see the away side peak. This shows that both in forward and central forward correlations. So one is the rapidity of the pion, and another one is the rapidity of the virtual dilepton pair. This has been published some time ago. Now let me go to the results on the direct photons, which is a topic of the current talk. So it is here on the figure 18, when you see that at RIC, we should be able to see the dip more likely in PP than in proton gold if we measure mid-rapidity pions and trigger on forward photons. But once we measure the pions emerging with rapidity 3 and trigger on photons with pseudo rapidity 3 with sufficient PT, say 1 GeV, we see the double peak structure. So the dip at at the delta phi equal pi, also in proton nucleus collisions. On the slide 19, I show how these azimuthal correlations will look like at pseudo rapidity of photon 4.4 and the rapidity of pion 4.5 for 4 different nuclei. Top is the hydrogen or proton, then you have oxygen, argon, and lead. The growth of the saturation scale with A as A to the 1/3 leads to decorrelation. So which means that the dip and all the peak goes down, and this depression behaves like a to the power minus 0.2. And last but not least, I also want to show you the result of, so up to now, all what I have shown on the correlation function was using GBW parameterization. Now with AMQS parameterization, which is shown on the slide number 12, we can see that there is a big difference when you go to really very forward direction, which means eta 6 and pion rapidity 6 for PT bigger than 3. Both models predict similar behavior and differ mainly in the region dominated by the leading jet fragmentation. So let me go to my conclusions. I have shown you, hopefully, that detailed phenomenological analysis of prompt photon production at RIC and LHC was done in the framework of color dipole approach. 3 or 2 different phenomenological saturation models for the dipole target scattering, GBW, CGC, AMQS, in the nuclear case, GM and RCBQ, were used to analyze the transverse momentum spectra of prompt photons in PP and PA collisions. Both in PA and PP, we have found a characteristic double peak structure of the correlation function around delta phi equals pi between back-to-back produced real photons and hadrons, in our case pions, emerging either at large forward rapidities or to a lesser extent when one of the particles is at mid rapidity. This double peak at delta phi equal pi appears to be strongly sensitive to the details of the theoretical modeling of the saturation phenomena in QCD, and therefore we recommend that the measurements of C delta phi at different energies at RIC and at the LHC should be done, because they will be useful when probing the underlying dynamics and setting even stronger constraints on the saturation physics. Thank you for attention.
Thank you very much for this talk, Mikhail. And I don't know if there are any questions from the audience. Okay, I think it's very late for you guys. So I thank actually all of those who stuck around with us to this hour. I know we are half an hour past our time, so I think it's a good time to end the session. I would like to thank all the speakers who have contributed to today's session. We had very nice talks, and thanks for all the effort you put into preparing these talks for us and for everybody else. We hope to see you in the next sessions, and yeah, have a nice evening.
Bye.
Bye-bye.
Bye-bye.
Hello, Agnieszka. So if you want to try, you can try to share your
Can you
slides.
hear me?
Yes,
okay.
I can.
And okay. So now I can try. So this is my Hadron. Okay. Share the screen. Okay. And now select. Something happened. So I have a now full screen, but I don't know. Okay. Meeting.
Yeah, maybe try to go back to your
New
PDF
share
viewer.
Screen. Okay,
And,
so
yeah, and I think try
now,
Control L maybe.
Control
Go to
L.
full screen.
I have full screen now.
Okay, so try to switch the slides.
But new share and select a window or application screen. But it doesn't work. I have this PDF on my desktop, And now I have open.
And maybe go to the menu. Like what are the options in the menu of the application for in this PDF browser, like viewing the PDF files.
Share computer. Sorry, but share. And
now I see just the okay, now I see the slides, but still I think it's not full screen. Or can you switch to the next one? Next slide.
It's not full screen.
But okay, try to switch to the next slide.
Next slide, okay.
Yeah, it's you like scroll down. There should not be the transition between like
So I don't know. I have a full screen, but I don't know what I should do now.
But
new share, your screen sharing. So stop share. So now you can you now see something, or I don't know?
Now I see your desktop.
Not slides.
No slides.
And now?
Now I see the slides, but as before.
So what are the slides? Because I have a full screen on my desktop now.
So you cannot see anything else than the slides?
When I don't know, meeting info, I couldn't, I couldn't open this now. New share. So I couldn't see this. I see the mute, start video, participant, new share, but copy. Maybe stop share. And now I will try again. Sorry that I trouble a lot, but this is my new laptop and I have here only Windows and I use it first time because I used to use Ubuntu, but I didn't, install yet. So maybe share screen. And now?
Yeah, I see it, but I think it's still not full screen.
Maybe you could change it for full screen, but how to do? Because I have a full, maybe, and now?
Yeah, but now I see just a part of the slides, yeah. But do you have some menu on the top part, something like file or something?
So I have this Adobe Reader Touch.
There's enter full screen. This you right?
New share, pause, note, remote, stop share, maybe stop share. So I don't know what is the. I have this PDF file on my desktop, and I can open it with
great.
Adobe Reader. And then it's a full screen. And then I should share screen, yes?
Yes.
But when I do like that.
Jak je to s tím? Sorry.
And now? It still doesn't work?
Now I see your desktop. No slides.
So, and now?
Now I see the slides, but can you try to switch to the next one? But maybe try to, what have you pressed to go to the next one?
Page down, page down.
Oh, page down. Because, you know, there's still, yeah, you can be like in the middle of the, somewhere between the slides. That's not good. You should go from one to the other without this transition.
I really don't know. I'm sorry. But why it doesn't work? Stop share. It's okay. I really don't know. You're sharing, new share. And then I should choose a screen or advance. I don't know, share computer sound, share. Can you hear me?